just to present to you this laboratory number 31. Sim. Então tá. Então vamos de novo. In English and in Portuguese. So since this is the 7th workshop and it's an international one, this workshop, all speakers will talk in English. So just briefly, my name is Wanderson Rocha. I'm a full professor of hematology in the University of São Paulo, and I am the director of the Laboratório de Investigação Médica. This means Medical Investigation Laboratory number 31. And the subject of this workshop will be natural killer cell-based cancer immunotherapy. Just briefly, I'm going to present the laboratory number 31. We have a total in the University of São Paulo in Hospital das Clínicas, 66. These are laboratories that are linked to the clinical and the basic science. So in fact, the laboratories, the aim is to put clinical staff and medical doctors with scientists. We are the number 31, and our laboratory is called Laboratório de Investigação Médica em Patogênese e Terapia Dirigida em Oncoimunohematologia. It means that we are working with oncology, hematology, immunology, and cell therapy. I am the director since May 19, and we have other investigators since then, Professor Barbuto, Professor Eduardo Rego, Dr. Israel, Juliana, Dr. Sergio, and many others that I'm going to present later. So for this workshop, we have done already about 7 workshops since I arrived as a director, and you can see that we are continuously increasing the number of participants all over, not only in Brazil, but in many other countries. And as you can see here, how we have asked, how did you hear about this event? And many on Instagram, indications, WhatsApp, LinkedIn, and of course, the information has passed among many other places. So these are the participants. We have 16 countries here for this workshop. You can see in Brazil, in South America, in Australia, in Europe, and in United States. And these are the numbers per states in Brazil. Most are in São Paulo, but many other states are in Brazil. But of course, mainly in Southeast. So we will try to increase the participants in other states of Brazil, mainly in the North and Northeast. So we have also asked which is the background of the participants. You can see here, this is very interesting that we have about 140 medical doctors, but most are, of course, linked to basic science, biomedicine, biology, pharmacy. So we will also try to increase more medical doctors and more scientists for the next workshops that we try to do about 2, 3 or 4 workshops a year. And we are very open to suggestions for the next one. So just to show you, we are really increasing the number of participants of the group in the cell therapy lab. You can see that we have now 1, 2, 3, 4, 5 PhDs. Rodrigo, who is a group leader of this laboratory, he has been working in France for many years, and he is in charge mainly of biology of macrophages, monocytes, and the dendritic cells. Samuel, who is a lab coordinator, and he is next week going to Washington for a 1-year period to work with Catherine Bollard in Washington. And he is in charge more of NK cells, and he is going to present all the speakers. Tel He's also a lab coordinator. He's a PhD, and he's in charge of CAR T cells. Rafael has just joined our group. He's immunologist, and he's working also in immunology of hematological diseases. And Dara she's also a PhD, and she's in charge of all the project managers as a project managers, and to try to increase the resources that we have. And as you can see here, we have many other students, postdoctorates and PhD students. I'm not going to show everybody, but I would like to thank Maria Paula, who has organized this workshop here. So which are the main lines of research? We have the generation of CAR T, CAR NK, CAR myeloid, and CAR iPS cells for liquid and solid tumors and infectious disease, HIV, HTLV, EBV. We have also projects on gene therapy for sickle cell disease. And we have already some funding projects. This is the National Program for Oncology that we have since last year for the project on CAR NK and CAR macrophages. We have the National Council for Scientific Research. We have the Foundation of São Paulo for Scientific Development. We have also a very good and nice collaboration with the Cell Therapy Lab at the University of Ribeirão Preto. We have many collaborations with INCA in São Paulo and outside with Marcos de Lima, Gui Savojo, Álvaro in Spain, Boro, and of course, Lucia, Silla, and Dean Lee, who has provided some NK line cells for us. So welcome to the 7th workshop. This is the program, and I'm going to present to you Lucia Silla, who is Brazilian. She is a professor of hematology at University of Rio Grande do Sul, and she has a great experience in the biology and clinical use of NK cells. So Lucia, welcome, and now you can say what you are doing, and then Samuel will present the speakers. Thank you very much.
Well, thank you very much for the invitation to be here in such a nice and high-level group of scientists and doctors. Well, I am, as you said, a full professor of medicine in the Federal University of Rio Grande do Sul, and I am the head of a GMP facility where our main focus is on the investigation of the clinical utilizations of NK, non-genetically modified NK cells. We ran already a phase 1 study. Now we are getting ready to get it to the phase 2 study of the same, protocol. With some variations, and we actually are planning to launch a Brazilian protocol of non-genetically modified in the academic environment. It will be an academic study. And we also study sickle cell anemia for a long time, and mainly on the molecular abnormalities that can define the clinical picture of that particular patient. I'm very happy to be here. Dean Lee is a long time
Collaborator,
friend, Marcelo too, and all of you, Lucila, and I'm very, very happy and looking forward to listen to you guys. Thank you very much.
So thank you very much. Samuel, please, it's your time.
I represent Fernando because they have a lot of noise there in the faculty now. Pleasure to us to introduce Professor Fernando Guimaraes, It's associate professor and principal investigator at the University of Queensland in Australia. So he is in the night there, so it's a great pleasure to have you here. And so Professor Fernando is studying the role of NK cells in the development of metastatic cancer and persistent bacterial infections. And we met him the last SBI last year, and we invite him. It's a great pleasure. Thank you very much, Professor Fernando.
Thank you, Rodrigo. Can you hear me well and also see my presentation?
Yeah, very well.
Wonderful. Well, thank you very much, everyone, for the opportunity to come and speak to you. It was a pleasure to meet Samuel and Rodrigo last year, and what a great conference. And so those are my disclosures that don't impact anything that I will speak here today. Just to give you a bit of a background on myself. So I'm originally Brazilian from Curitiba, and I did my master's there, and then I moved to France to do my PhD at the Institut Pasteur Paris. And in Paris, like I was lucky enough to meet someone like Nick Huntington while he was still doing his postdoc there at the Institut Pasteur. And I ended up moving to Australia, and I did my PhD with him. And today, Nick is a professor at the Monash University. He left the VII, and I became like a group leader and associate professor at the University of Queensland. And I kept my ties very close with Brazil to, like, after the conference in São Paulo last year, I went to Curitiba for taking part on the program of internationalization of the Federal University of Paraná, where I was providing them with like postgraduate trainings on immunotherapy and also the professional development for who are in Brazil thinking on going overseas for doing a career over there like I did. So I'm passionate about what I do, and I have been mentoring multiple people from their undergrads to their postdocs and becoming group leaders, Brazilian people that are excellent and wanted this kind of opportunity. So I'm very glad that I had this opportunity myself, and I continuously keep to giving back to people who want to. So my team today, we are a highly international and young group. So my lab was established in September 2019 at the University of Queensland, just before the pandemics. Today I have 5 PhD students and 2 postdocs, including one that it's in a sandwich postdoc from the PUC Paraná, the Pontificia Universidade do Paraná, and is a pathologist that came to spend 1 year with us. We are also open for this possibility, like people that are doing their PhDs there or postdocs and want to come for overseas for a period for collaborating with us. We opened our doors for this kind of collaborators too. We are based on the University of Queensland, which ranks the number 36 on one of the best 100 universities of the world. And within the University of Queensland, we are based at the Fraser Institute. The UQ, University of Queensland, has multiple different institutes. The Fraser Institute, it's a notorious institute that was named after Ian Fraser, who was a professor who discovered and developed the HPV vaccine Gardasil, which today is a hallmark on immunotherapy that it's used worldwide for curing this disease. Our vision there is that we can awake the Q inside of us through immunotherapy. And we have been building capacity in biomanufacturing technologies, is also developing multiple different solutions for trying to bring to patients that suffer from hard-to-cure disease. My group, it's named Translational Innate Immunotherapy. We are heavily focused on natural killer cells. I have been studying those cells in the last decade, but we're not restricted to. So I have like a number of other projects that are unrelated to the NK cells. We are immunologists, and we try to be not closed-minded, but open-minded about which kind of questions that bring us where we want to go. We have like 3 research arms, one in cancer immunotherapy to try to develop new immunotherapy, one that it's a more basic biology arm where we try to understand the regulatory signaling of the NK cells. There's a lot we do not understand yet about why their functions are prevented in the tumor microenvironment. And another one, which is inflammation. I did my PhD in sepsis, in bacterial sepsis and NK cells. So I do have like a background on inflammation. And that was particularly productive on the last couple of years on the COVID space, where we published a number of publications on that topic. Today, I will focus more on cancer. And cancer immunotherapy, I'm sure many of you might know, but some of you might not know. Immunotherapy has started a long time ago, starting by the discoveries of William Coley, who tried to identify that the elicit of immune responses on tumors by injections of bacterial extracts would make like an immune response and make some of the patients actually get cured from those cancers. The discoveries of William Coley lost momentum in oncology because in parallel, Marie Curie was also the developer of the radiotherapy, which really kicked off on the field. And during this long period from the 19th century to not long ago, like chemotherapy and radiotherapy were the dominant areas of interventions on oncology. And I wouldn't be lying if I say that oncology 30 years ago mainly did not believe that the immune cells could do anything at all on cancer microenvironment. But the field has changed. And some of the promoters of that immunology can really make a difference on cancer were the Nobel Prizes in medicine, such as Tasuku Honjo, the discoverer of the anti-PD-1, and the PD-1 checkpoint inhibitor, and James Allison, the discoverer of CTLA-4 as the function of checkpoint inhibitor, the developer of antibody from discovery to translation in patients. And the same year, we had the Nobel Prize in Chemistry by Greg Winter, who developed technologies that allow antibody development against those checkpoint inhibitors. And the results of the phase 3 clinical trial allowed FDA approval of the anti-CTLA-4 in 2011. And since we had like a hold on, because multiple clinical trials have been happening at this stage, and then a cascade of FDA approvals by different immunotherapy interventions started to kick off. And today, we are pretty much the era of the immunotherapy. And immunotherapy tried to fix the body by using their own immune system. And this has been highlighted by a number of different prestigious journals. We all recognize immunotherapy as a critical pathway to cure diseases. And it's important to realize that most of the immunotherapies are actually T-cell based. The immunotherapies that are available overseas, like many of them are trying to elicit the T-cell response against cancer. And there are reasons for why T-cells have been on the hotspot for such a long time, and not other cells, such as natural killer cells, which is what we study. So NK cells, they are understudied, underappreciated, and they are pretty much neglected. So they were until now. So my own experience taking a metastatic melanoma stage 3 from a patient from the Peter Mac Hospital and making a flow cytometry preparation, I could see that the infiltrating immune cells on this melanoma, a minority of the lymphocytes would be NK cells, maybe 3 to 5%, and the majority of them would be T cells. People have noticed this before. I'm not the first one. And this also caused the NK cells to be neglected because they're a minor population infiltrating of the tumors, and people focused on the T cells. They're easy to manipulate, they're adaptive, and they're also the majority of the cells. They're the big players. But if you think again that from this minor NK cell infiltration, 100% of them will express activating receptors able to recognize class 1 deficiency or stress ligand expression, such as NKG2D or killer ligands. 100% of these NK cells might recognize these melanoma cells. And if you think about immunology, the adaptive immunology, that we need like the antigen-specific clonal expansion of T cells, maybe less than 1% of these infiltrating CD8 T cells are actually neoantigen specific. So we could reverse this equation by saying that we actually might have more effector NK cells compared to CD8 T cells in the tumor microenvironment, such as this one here. So the impact of the NK cell infiltration and activity
I guess I lost the presentation. It's just on my end. I guess I lost the presentation. It's just on my end.
Okay.
I think Fernando's having trouble to connect.
Hi everyone, I think we can wait just a little bit, just a few minutes to see if Fernando can reconnect. I think his internet connection crashed. Sorry about that. I'm trying to reach Fernando here. Do you think we can maybe start with Marcelo and see if Fernando reconnects later, and then he can finish his presentation? So we don't lose that much time of the workshop. What do you guys think?
For me, it's okay. So you guys.
Okay, Marcelo, I think you can go ahead and share this. Oh, sorry. First, I'm going to introduce you to everyone. Let me open my cam here. So everyone, let's keep going with the presentations. If Fernando reconnects, we can continue from where he stopped. So I'd like to introduce Marcelo. Well, thank you very much for accepting our invitation, Marcelo. It's a pleasure to have you with us on our workshop. Marcelo is a Brazilian. He is a biologist. He worked in the School of Medicine of Ribeirão Preto, here in Ribeirão Preto in São Paulo, at the University of São Paulo. He got his master's degree in basic and applied immunology, and he got his PhD degree in cellular and molecular biology at the same academic institution. He is now an immunologist and part of Dr. Dean Lee lab at Nationwide Children's Hospital. And his focus of study is how immunotherapy mediated by NK cells can tackle pediatric cancer, especially by using gene-modified NK cells by some techniques like CRISPR and Cas9. And it's a pleasure to have you, Marcelo. So please.
Well, thank you so much, Samuel, for the kind introduction, and also thank you so much for the invitation. I will try not share my video, so in this way I will try not crash, so to avoid any further problem. So well, it's a pleasure to be here. It's a pleasure to share our research in Brazil and be able to collaborate with all of the great scientists that we have. I'm very optimistic with science in Brazil, and then I'm always looking forward to do collaborations and doing presentations. As Samuel said, I'm research scientist and master coordinator at Lee Lab under supervision of Dr. Ding Lee at Nationwide Children's Hospital. And today I'm going to talk about part of our research that we do in our lab. And the title of my talk is, excuse me, TGFβ-Imprinting of primary NK cells decrease CD38 NADAs, promotes reprogrammed tissue-resident Adressin profile, improve cell killing, ADCC, and metabolism. I hope today I will be able to show you guys that TGFβ-Imprinting enhanced production of pro-inflammatory cytokines, loss of sensitivity to TGF-beta immunosuppression by downregulation of SMAD3 signaling. We were able to see markedly improved of serial killing, also reprogrammed tissue-resident Adressin profile. I hope I will be able to show you some preclinical model that we have in mouse. We also have some in large animals that are dogs that I'm not bringing today. Also, we're able to show that imprinting increased oxidative phosphorylation capacity for improved metabolic fitness in our NK cells. And also, imprinted NK cells are protected against fracture side effect mediated by daratumumab. This is our disclosure, and I would like to share with you guys that I have some QR codes from our publications, and then if you guys want to know better about some of our publications, just have your phone in hands and take photos of this QR code. Will be a pleasure for us. So this is one of the figures that we love the most, and why? Because this is one of the few pictures that has NK cells in the center of immunity. And then as we are NK cell lovers, we know that NK cells are in the center of immunity. So here we can see that, and then I'll have my pointer here. Oops, sorry. No, it's not that. I need a laser point. Yes. So we have NK cells here having this crosstalk between other immune cells, for example, B cells, T cells, TCD4, TCD8, and then also has this connection with NKT cells, especially by secreting cytokines. We can see that NK cells can secrete interferon gamma that will be able to activate T cells. And also we know that NK cells, they are able to induce immunopressure on the cancer cells into the tumor microenvironment. But we also know that in the tumor microenvironment, there are a lot of subproducts and also TGF-beta that's secreted by tumor cells that will induce immunosuppression to NK cells. So also we know that in the tumor microenvironment, we have decrease of NKG2D. That's a very important activating receptor of NK cells. We also know that there is decrease of CD16. That's a very important receptor that will recognize antibodies through FC receptor. Also, we have decrease on perforin that will be able to do cell lysis or induce cell lysis, and also decrease on interferon gamma that I just mentioned to you that is able to make this crosstalk with the other immune cells. So since that TGF-beta is a problem for NK cells and then its activation. So we know that, as I mentioned, in the tumor microenvironment, TGF-beta is highly secreted. And then here I'm showing you guys several different tumor cell lines. And then here I'm showing you mRNA levels of TGF-beta. And then we can see that from the high to the low TGF-beta secretion on the tumor cell lines, all of them are higher than normal tissue. And then this is just secretion of TGF-beta. So it's really a problem for immune cells activation. So, as I mentioned, in our lab, we work with NK cells, and then we are able to isolate and expand NK cells. How we do this? We are able to isolate NK cells from buffy coat, and then after collecting these cells from buffy coat, we are able to expand our NK cells using feeder cells, and then we use K562 with membrane-bound IL-21. And then we do this expansion during 14 days, and every other day we add IL-2 in 50 IUs every other day. To induce our TGFβ-imprinted NK cells, we also, together with IL-2, we also add into our culture TGF-β in 10 nanograms every other day. And then this is just to picture you guys how the activation and expansion happens mediated by membrane-bound feeder cells. So we have here IL-21 that will bind to IL-21 receptor, and then will stimulate STAT3, and then through STAT3 signaling we have our proliferation and expansion of NK cells. So we know that TGF-β, for TGF-β signaling, we have recruitment of SMAD2, SMAD3, and SMAD4, and then we have this trimer being engaged, and then after this trimer being translocated to the nucleus, we have a lot of different genes being transcribed. So all of this should tell you that we have some important proteins that are recruited for TGF-β signaling. And then how we are able to see that with TGF-β imprinting, we are able to overcome TGF-β signaling. We're able to see that TGF-β chronically stimulation of NK cells leads to blockage of TGF-β signaling by blocking SMAD3 signaling or eliminating SMAD3. And then this is just to show you guys that by Western blot, our TGF-β imprinted cells, they lack completely SMAD3 by Western blot. So in the same, this was a publication that was published before my arrival in the lab, and Dr. Foltz was able to show that imprinting of NK cells was also able to induce cytokine hypersecretion. Especially, I would like to bring your attention for GM-CSF, interferon gamma, and TNF alpha in our imprinted NK cells that are the red dots here. Also, imprinted cells, they are not sensing or the chronic stimulation of TGF-β in NK cells was able to promote this escape of TGF-β in NK cells. What we have here, we have percentage of lysis of tumor cells, of control NK cells, and control NK cells in presence of TGF-β. We can see that we have decrease in percentage of specific lysis on tumor cells. But TGF-β imprinted cells that are able to overcome TGF-β signaling, they are not sensing the deleterious effect of TGF-β into the culture. So what we start to do in our lab, we decide to look for long-term killing in with our TGF-β imprinted NK cells. And I would like to bring your attention for TGF-β imprinted cells here. That's blue and pink here, that we have two different ET ratios. And we can see that both 2:1 and 0.5:1 TGF-β imprinted cells, they're able to kill way better than wild-type NK cells that are red and green here. So suggesting that TGF-β imprinted NK cells, they are able to overcome indeed the deleterious immunosuppression of TGF-β in the system, and then they with this data we are able to see that they're not getting exhausted in other hand, different from wild-type NK cells. We are able to see this in both AML cell lines, CML cell lines that are our K562, and also we're able to see very similar data with solid tumors that are melanoma cells that are MEL33 and MEL41, suggesting that those cells are very versatile, and then they're very important tools. And they had a better serial killing. So next, we decide to look for mRNA-seq analysis, and then we can see here that our RNA-seq analysis showed that we had more than 1,700 genes that are different expressed, and then we can see by PCA analysis that we have two distinguished groups. That is untreated, that is our standard NK cells, versus our treated, that's our TGFβ-imprinted NK cells. Also, by gene expression, we can see clearly two distinguished groups here, and then some genes being upregulated and downregulated. And also, by this volcano plot, we can clearly see some genes that are downregulated and some genes that are upregulated. And I would like to bring your attention for CD300 and ETGAI, that's CD103, that are two membrane proteins that we are now using these two proteins as markers to use and to prove, to validate our TGF-beta model when we have our GMP product, just to have this this data as a fast result. So also our RNA-seq analysis showed that we have gene expression, differential expression of some Adressin profile. We can clearly see two distinguished groups here showing upregulation and downregulation in its specifically group. And then I would like to bring your attention for some Adressins that are, or chemokine receptors that are increased here, especially CCR4 and CCR7 that are upregulated in our TGFβ-imprinted cells, and also some integrins that are upregulated in our imprinted NK cells, suggesting that our NK cells, they should have a better migration to the tissue. With that, we decide to move to a mouse model, and then here we are using a CHLA tumor cell line that's a neuroblastoma cell line, and then here we are using an NSG mouse to evaluate the effectiveness of our TGF-imprinted NK cells. So our mouse received tumor cells, day 0, and then we induced it. We did adoptive transfer of NK cells twice a week during 4 weeks, and then we also evaluated the tumor progression during these specific dates here. And then we can see clearly, I would like to bring your attention here for day 38. We can see clearly that both standard NK cells and TGF-beta-imprinted NK cells, they have lower tumor burden when we are compared to tumor only or our control group. And then here's just to show you guys that the time course of our tumor injection, and showing that TGF-beta-imprinting retains a very similar tumor control as standard NK cells. So we saw that we don't have difference between wild type and or standard and imprinted NK cells. But we saw something very interesting when we start to open the animals. And then I would like to bring your attention for this image here. And then here we have some livers from the coming from the injected mouse. And I don't know if you guys can see from your screen, but we can clearly see that control group or tumor-only group, they have way more liver mets when we are compared to both standard NK and TGF-beta-imprinted NK cells. But if you look closer and compare TGF-beta-imprinted NK cell group versus standard NK cells group, the TGF-beta-imprinted NK cells group are even more protected than standard NK cells, suggesting and then coming together with the importance of Adressin, and then suggesting that our TGF-beta-imprinted NK cells, they are able to migrate more to the tissue. So next, we also, from our RNA-seq analysis, we were able to see that CD38, that's NADase, is downregulated in our NK cells. imprinted NK cells. And then here we have in black naive NK cells, and our expansion system is able to decrease CD38 by itself. And how it happens, we know that our expansion induced STAT3, as I mentioned to you in that figure, and then somehow our TGF-beta imprinted NK cells or TGF-beta resistant NK cells, they also have decrease of CD38. So we proved that by flow cytometry and looking for protein expression. Here we can see decreasing percentage of CD38 in our imprinted NK cells, and also by MFI. And we decided to understand how this is happening. And then I just mentioned to you that our expansion system induced STAT3, and knowing that STAT3 and STAT1 pathways, they have this competition, and then knowing that STAT1 is important to induce CD38, we decided to look for STAT1 expression, and indeed we have decreasing STAT1 expression in our TGF-beta imprinted NK cells. We know that TGF-beta, previously in our lab, we published a paper showing that decrease of CD38 was able to improve NK cell metabolism, and then we decided to walk the same path. We looked for metabolic features in our expanded NK cells versus our imprinted NK cells. And then we can see clearly in red here that imprinted NK cells, they have higher oxidative phosphorylation. And then when we are looking for glycolytic pathways, we don't have difference between standard NK cells and TGF-beta imprinted NK cells. And when we do this ratio, OCR versus ECAR, we can see clearly that TGF-beta imprinted NK cells, they prefer to do oxidative phosphorylation. As I mentioned to you, we published before that deletion of CD38 of human primary NK cells eliminates or I mentioned that was able to improve metabolism in our NK cells, but this is the title of our paper. We're able to see that deletion of CD38 was able to eliminate daratumumab-induced fratricide and boost their effector activity. So we decided to look if or understand if our TGF-beta imprinted NK cells, they were able also to overcome the fratricide effect mediated by daratumumab. Why we are using daratumumab, if you guys are familiar with that, daratumumab is a standard care of multiple myeloma, and daratumumab is an anti-CD38 antibody. This antibody will bind in all the cells that express CD38. Both tumor cells and NK cells, they were able to express CD38. In this way, NK cells through CD16 in the very beginning, they were able to recognize antibody and were able to induce killing. This we call event we call as fratricide. That means brother killing brothers, or NK cells killing NK cells. We're able to see that CD38 in knockout NK cells, they do not suffer fratricide effect. And then in our system with TGF-beta imprinted NK cells that also have decrease on CD38, they are able to overcome this fratricide effect. And then indeed, we are able to see here, we are able to reproduce that standard NK cells, they have a decrease on percentage of live cells in presence of daratumumab, and then this is the fratricide effect. But TGF-beta imprinted NK cells who lacks or have decrease of CD38, they are protected against fratricide. And then this is just showing you the percentage of live cells, and then here kind of the same thing, just showing the percentage of dead cells that's just pictured the same data. So after that, we decided to look for ADCC, and then we were using 3 different cell lines here, 2 TALL and 1 multiple myeloma cell line, and then comparing wild type versus TGF-beta imprinted NK cells, we can clearly see that TGF-beta imprinted NK cells that are able to overcome fratricide effect, they also have improvement in ADCC. So as conclusion, I hope I was able to show you guys that TGF-beta imprinted was able to suppress CD38 improved oxidative phosphorylation and elimination of fracture site effect, increase NK cell potency, tissue homing by increasing Adressin, and we're able to induce serial or improve serial killing. Therefore, TGF-beta NK cells combined with CD38 targeting may be considered for CD38 positive malignancies. And then I would like to first thank you all for your attention, for your time, especially for the invitation, and the lab for all the support, especially Dr. Dean Lee that's here, and all the funding. Thank you.
Thank you very much, Marcelo. That was a really great talk. So now we have some time for short time for questions, maybe 5 minutes, some 3 or 2 questions. I have a question from the audience here. It's from Lucas. So he said, Marcelo, did you note whether there are differences concerning TGF-beta imprinting between different subtypes and sources of primary NK cells?
Can you repeat the question? So I had a break here.
He asked you if you note, did you note whether there are differences concerning TGF-beta imprinting between different subtypes and sources of primary NK cells?
Wow, that's a great question. Thank you so much, Lucas. So for us to be able to induce imprinting of NK cells, we are forced to do expansion of our NK cells. So we as our lab works specifically with PBMs, NK cells coming from PBMCs or coming from Buffy coat. This is the only source that we were able to generate imprinted NK cells. So in this way, we're not able to do this comparison with, for example, primary NK cells, because primary NK cells, after 14 days of expansion, or after 14 days of, even if we don't do the stimulation with K562s or feeder cells, they will barely survive after these 14 days. So it's kind of very hard for us to do this kind of comparison, but I guess the short answer should be I have never done. And Dean is here. I don't know if Jennifer was able to do anything before my arrival in the lab, but I guess the short answer is I have never done this.
Lucia has a question, Samuel. Go ahead, Lucia.
Yes, but what I understood, Marcelo, and that, well, congratulations. This is a great talk. This is a great work that I really am looking, for some time. What I mean that I'm always following you in your work.
You're my friend.
Yeah, well, no, you have a great work. What I would like to understand is when you get the imprinting, when you imprint NK cells, you do that with the expansion platform utilized for normal NK cells, non-imprinted NK cells, don't you?
That's correct.
So can't you compare the two of them? Because it would be the wild, it's not wild probably, but the wild type NK cell and the imprinted NK cell.
So sorry if I miss anything. So what we do this. So indeed we use the platform feeder cells to expand our NK cells. So all our comparison that we do here during my presentation, we are comparing imprinted NK cells that has faced both feeder cells, IL-2 and TGF-beta, right? Mm-hmm. And we are comparing against the one that receive only IL-2, and feeder cells. This is our comparison. So we are, when I'm comparing TGFβ-imprinted versus standard, or we can call wild type NK cells, we can call standard. So it's always in presence of chronic stimulation of TGF-beta or just the regular expansion that we have. I guess a question that I had from Lucas was if we had different sources of NK cells. What I understood is, for example, if we did imprinting with cord blood, for example, with IPS, I have never done with those NK cells. And the thing that I brought up was the non-expanded NK cells that would be the primary NK cells. So with primary NK cells, first, if you do chronic stimulation with primary NK cells, we will not be able to have viable cells by the end of 14 days in presence of TGF-beta.
Okay.
So, yeah, I guess that. But I don't know.
Yeah. You mean by primary NK cells, you mean resting NK cells, right?
Yes, just collected, just isolated and resting in presence of TGF-beta. I don't believe they will survive for 14 days. They might survive for 7 days, but we saw from previous data in our lab that to induce and to generate a strong and lasting imprinting phenotype, we need to do this stimulation for 14 days.
All right. Thank you.
Yes, thank you for your question.
So, Marcelo, we have just one more question so we don't get too far behind in the schedule. So we have a question from Rafael from the audience. He's saying, Marcelo, great presentation. Do you think SMAD3 knockout NK cells would have similar function as TGF-beta-imprinting NK cells?
Well, that's a great question, and I'll try to open my camera here to answer this. So that's a great question. Thank you so much. And then actually, this opened up a Pandora box for us, and then Dean is here. He can try me if he wants, but open up a Pandora box for us. We're just believing 100% that this should be the pathway, and then by just knocking out SMAD3, we would be able to generate the same or similar phenotype, and then ended up that we couldn't, because that is a canonical and non-canonical pathway, TGF-beta pathway. So when we are knocking out SMAD3, we're just knocking out or getting rid of the canonical SMAD3 pathway. And then since that something is happening through the non-canonical pathway as well. So in other words, we were able to generate this SMAD3 knockout, and then even in this SMAD3 knockout, we were able to induce TGF-beta-imprinting. So it was kind of a very, very interesting data that we are working on that still. So Asgi, that's our PhD student, is working on that. But yeah, it's very, very interesting. And then we are very excited. I keep telling Dean that I'm very excited with negative data. So we just have more things to dig and then to try to understand better the science, and then that's what we do. That's what we do in our lab. And then, yeah, thank you so much for your question. I'm happy to hear anything else.
May I say just a little thing?
Yes,
I
absolutely.
think negative data is fantastic.
Yeah, I believe that.
It's it's the point. So that path cannot be utilized, and that's it.
Yep.
Congratulations.
I agree with that 100%. Thank you so much, Lucia. Well, thank you so much, all of you. Thank you, Link 31, for the invitation. Samuel and Vanderson, was a pleasure to be here with you. Lucia as well. It's always a pleasure to see you. And then I hope we can collaborate and have more conversation throughout the year and the years to come.
It's a pleasure, Marcelo. Thank you very much. Samuel is going next week to US, so he, if it's possible, he can even visit you. I think it's very nice to establish this collaboration. Thank you very much. And
absolutely, thank you
as well.
Thank you so much, Marcelo. Let's do some work together, for sure. And so I'd like to call Fernando back. He was able to connect again with us. Hi, Fernando, are you there? I think you're on mute. If you... Can you hear me, Fernando? Let me see if I can reach him out.
This is because Australia is too far.
Yeah, it is. And
it's too late, so he might have dropped on his computer.
I think the internet got slow after midnight. I'm trying to reach him on his cell phone. Let me see if he answers me. Hi, Fernando. Yeah, I think he's trying to connect. Just a little minute, guys.
Can you hear me okay?
Yeah, now we can hear you. Do you want to try?
Yeah, good internet here, actually. I don't know what's going on.
No, it happens. Everything happens when we're live.
Yeah. Okay. Well, I can try to come back from where I was. Can you see my slides?
Yeah, we can see it. Perfect.
Wonderful. I will, if by all means you don't hear from me, just text me again and I will try to reconnect straight away.
Okay, no problem. Go ahead, please.
Awesome. Yeah, so I believe I stopped around here on the last time. So we created mouse models where we can define the role of NK cells in vivo on immunocompetent mouse models. One approach was to delete the anti-apoptotic protein MCL1 on specific on NK cells. That's a protein it's anti-apoptotic and it's inducible by IL-15. Interleukin-15, it's something that the NK cells, they need to survive. They can't survive overnight without it. And when we delete MCL1, specifically in NK cells by the NCR1 Cree mouse, we lose all the population of the NK cells from these mouse and everything else is intact. The macrophage, the T cells, the B cells. If we inject in this, in a wild-type mice, about 50 then intravenously.
Não voltou. Hi, Fernando. Hello. Hi, Fernando. Can you hear me? I think he just crashed again, guys. I'm just seeing if he's going to connect again. Or if we can just move on with the presentations so we don't get too far behind. Hi, Fernando.
Hi, everyone. So sorry.
Don't worry. Let's try it. Let's try once more. Yeah.
All right. Looks like my internet is misbehaving here today.
Saturday.
I know.
Saturday night. Everyone is on the internet.
No, it's
Can
okay.
you see my slide?
Yes.
Awesome. So I will try to talk quickly so then there's time. So bottom line is that we created mouse models of NK cell deficiency, and we can prove that these mouse models are heavily dependent on NK cells for surveillance of metastatic cells. Here, for example, it's melanoma. In the bottom, it's non-cell lung carcinoma. In the middle is breast cancer, where we inject the breast cancer intramammary and then we remove surgically. And then we can appreciate the metastatic seeding on the lungs of the mice, that it's really dependent of the NK cells to be there to control this. The speaker before me, Rodrigo, presented very well, like the background of the NK cells. I don't have to tell you much about all this suppressing and activating inflammatory agents. Myself, I'm very interested on TGF-beta too. So TGF-beta is a very important signaling pathway for development, for preventing systemic inflammation, among others. A knockout mouse of TGF-beta doesn't survive more than 2 weeks. It dies from systemic inflammation. So NK cells come to hate TGF-beta, as we just saw in the previous speaker that tailored it very nicely. We contributed with some papers in the field, and we also thought that our contributions were just addressing the tip of the iceberg. The TGF-beta receptor is a kinase that can phosphorylate more than other 500 different kinases. So the cell signaling, it's very complex between cell-to-cell subset. And why I'm talking to TGF-beta is that I was very interested on this paper in 2016 on Nature Immunology by Nick Huntington, my postdoc boss, where he discovered that IL-15 is an important activating factor that drives not only NK cell survival and anti-cancer immunity, but also the expression of CIS. And CIS is a checkpoint inhibitor. If you delete CIS, the NK cells will proliferate better, they will kill better, and people have been addressing that in a number of different interventions, including CAR NK cells. But what puzzled me here, and this is data from global proteomics, is that CIS knockout, they have the double of the expression of the TGF-beta receptor 2, suggesting that they might be more susceptible for TGF-beta signaling. And that's what for me was curious and worth to be studied more. And I did a collaboration with the third co-first author, Laura Dagley, who today is the manager of the proteomics facility of WIHI and a well-known expert on cell signaling. So we hypothesized that IL-15 drives the STAT5 pathway, making the NK cells express granzymes, MCL1, among the others, including CIS. And the TGF-beta receptor that it's suppressive might have a context here, which we don't know exactly what it is. So we got a project grant, myself and Laura, a new investigator project grant from the NHMRC, which is similar to the NIH here in Australia. And that allowed me to recruit the talented postdoc, Gustavo Rossi, to help us out here to try to understand what's going on. Among the different experiments we did, we also generated a double deficient mouse model of the TGF-beta receptor deletion in NK cells and also CIS all together. And here we injected a high load of V16F10 intravenously, 300,000. It can make like quite a number of metastases on the lung of the mouse. And we could observe upfront that the double deficient mouse model is highly resistant to this high load of melanoma. And on MC38, we, by ourselves, we have never seen a mouse model of NK cell dependence of gain or loss of function show a phenotype on MC38 subcutaneous tumors. Those are colorectal cancers that are highly used on studies like PD-1 or T-cell. And for us, for the first time, we actually saw a NK cell dependent mechanism, like providing an anti-cancer response on the subcutaneous mouse model, which is quite interesting. We repeated this again, and we killed the mouse in an early time point, and we could observe like a high infiltration of NK cells by single cell analysis, which were suggesting to have like less expression of the checkpoint inhibitor TIGIT and more expression of cytolytic proteins like granzymes, which is really interesting. This is a piece of data that was published not long ago in Cancer Immunology Research. There's a lot more happening on this topic, including in human cells. And other aspects that my lab is interested at the University of Queensland, it's a range of them, including ADCC. So as we have seen on the presentation before, highlighted very well that TGFβ can abolish ADCC. I'm interested in the topic. We published in Cell 2 years ago with the group of Fiona Simpson, the renaissance of the NK cells on ADCC. And that's a beautiful paper that we are now continuing by co-supervising Josh Wong, a talented PhD student, on how to weaponize NK cells even further with new antibody-dependent cytotoxicity. So we are in this topic. And on the chimeric antigen receptor, we also appreciate the evolution this has been made in the field. This game-changing paper by Kathy Rezvan in New England Journal of Medicine really highlighted that the CAR NK cells can be used allogeneic and can work well. And it doesn't seem to cause a cytokine response syndrome or neurologic cytotoxicity or other diseases like GVHD. So this really has shaken the field to show that NK cells can be really the way to go. And we are really interested on diseases, not blood cancers at the moment, but particularly pediatric sarcomas, which are really hard to cure. Sarcomas in Queensland, where they state that they live in Australia, they are a main death of kids, adolescents, young adults. And we believe we can target them with NK cells, and we have the generous support of the Queensland Children's Hospital to try to go towards on this disease. And one of the reasons why we want to focus on sarcomas is because this disease didn't have any new or significant therapeutic intervention on the market on the last 30 years. So it has been really like a good timing to try to approach that with a killer response like NK cells. And we have like been co-supervising like oncologists such as Natasha Omer, who is in the front line of treating those sarcomas. These bits of preliminary data that we can show that the high NK cell infiltration can really be correlated with enhanced survival on osteosarcoma kids. And we are betting that the cure mismatch has been a potentially good approach for trying to engineer cure mismatch NK cells even further for trying to infuse those kids. So this is an approach that we have been highly interested on. And we are able to generate CAR constructs, like for this example, APHA2. It is a CAR antigen that is highly expressed on sarcoma cell lines and sarcoma cancers. And when we make CAR NK cells expressing high amount of those CARs, we can appreciate the amount of killing that we have on sarcoma cells that express those antigens. And even in orthotopic mouse models of NSG engraftment with NK cells and the tumors, on the this is a rhabdomyosarcoma, intramuscular, so it's orthotopic. It goes metastasized to the lungs, and we can appreciate that when the mouse is treated with the NK cells, the metastasis is not so bad. So we are investing hard on this aspect, as many institutes have. Our institute also has dedicated good manufacturing compliant clean room, where we have tried to accelerate this development of these NK cells on a pre-GMP setting with a dedicated clean room for my group here at the Translational Research Institute. Other research interests that we currently have, during the pandemics, we contributed with quite a number of studies on spatial transcriptomics, spatial proteomics of the diseases of COVID-19. So we became really good on those multi-omics approach to try to understand what is the mechanism of disease. We were in the news recently because we got like a project from the Medical Research Future Fund to try to address this, to understand tumor microenvironment of cancers like sarcomas. Why are they poorly infiltrated by the NK cells, and how are the NK cells behaving within those tumors? Because we believe we can engineer them further according of what we discover on this big picture before we try to infuse patients with CAR NK cells. First, we should understand the disease a little bit more because we don't understand enough of this disease. And this is my group. We are located in Queensland on the state of the Great Barrier Reef in Australia. It is a beautiful place. We are a very young, motivated, and multidisciplinary team that embraces diversity. And we are always looking for new people to join us. So if there are talented people in Brazil looking for doing a PhD overseas, the UQ ranks number 33 on one of the best universities globally. And we are about to start a process of recruitment of international applicants. And our institute is the UQ Fraser Institute, named after Professors Ian Fraser, the co-discoverer of the HPV vaccine, which is an example of translation made by the University of Queensland, the Gardasil, who is used worldwide. And we hope to do the same in the nearby future. And you could be part of the team. Let me know if you have interest to come to Australia. You can always approach. And I welcome any questions you might have. And I hope my internet didn't fall during my presentation again. Thank you all.
Wonderful.
Thank you very much, Fernando. It all went well this time.
Wonderful.
Great presentation. Very interesting work you have there. And of opportunities for young people to join a great team, right? A great city to work and to live. So very, very good. And do you have any questions from the participants here? Dr. Lucia? You're on mute, Doctor.
Yeah, thank you. A wonderful work. Sensational. I liked very much, and particularly your approach of, and I would like to hear some more about that, but your approach on understanding the disease microenvironment to know how to do it, it's fantastic.
Thank you so much, Lucia.
Very, very nice. And, so far, the two speakers are going to speak here for our, I'm going to, steal them for our group of experimental research in Porto Alegre, which is a very strong. There are several lines, not only hematological malignancies.
Oh,
very, very interesting.
Fernando, very nice work. I have a question. Is there any clinical trial in Australia on NK cells? And what about other diseases?
Yep.
Are you working on?
Yeah, so there are two clinical trials at the moment in Australia, but they are not academic, they are industrial funded. One is an extension of Enicarta's clinical trial. Enicarta is a leading NK cell company from the US, so they also have their allogeneic NK cells being transferred for a clinical trial in one of the major hospitals here. But what's going on there is quite secretive because it's part of a major clinical trial globally. And there's another Australian NK cell company who is also trying to kick off Cartartics. They're also trying to do like an iPSC NK cell clinical trials. We would love to do a clinical trial, but we're not quite ready yet. So we're still trying to build up our biomanufacturing capacity for doing that. And what was the other question?
Was just...
yes, only for each disease do you have, are you working in the lab? For example, you have sarcoma, but for each other diseases?
For the grants that I have, I have a grant for sarcoma, one for neuroblastoma, one for blood B lymphoma as well. This is more for mouse models, and that's pretty much the funding that I have. I have published a number of other papers that I don't currently have the funding for those, but my priorities from now on will probably be towards the pediatric cancers.
Mm-hmm. So Marcelo has a question.
Hi, Fernando. Very nice talk. Really nice to see that you got very similar data and then using different models. So you do knockout, we do just imprinting. Forgive me if I missed something. So when you did your model, and then you mentioned about metabolism. So did you guys do any further experiment regarding metabolism? Do you know which kind of pathway is fooling your metabolic improvement? And also, I had something else to ask. Which pathway you guys can see that you are improving the metabolism?
Yeah, right. On the TGFβ, we have performed like a range of seahorse-based metabolic assessments, where we could clearly see that TGFβ could block the metabolism quite efficiently. The metabolism of those double deficiency and the TGFβ seems to be better on the double deficiency in responsive to IL-15. What pathway specifically, it's tricky. So we did try to do experiments like transcriptomics assessments, and it gives you hints about like metabolic function, but we can't fully be sure about that because it's RNA based, it's computationally. We do have interest on trying to pursue that even more. I even discussed the possibility of trying to do a phosphoproteomics assessment, which is a thought that I have, but I haven't done it yet. But I'm interested in the topic. If you have interest on discussing that more, I would love to hear your suggestions. If there's anything we can do to help you.
Yes, absolutely. We're very interested in understanding better, or further understanding what's happening with our TGFβ-imprinted cells and why they have this such nice better metabolism. So yeah, absolutely, I will reach you. So I'm just coming back to US on Tuesday. I will arrive on Wednesday, and then after that I will be able to contact you. And also I'll contact you, Lucia, so we can schedule that presentation for sure. Thank you.
Sounds good.
Okay, I don't think we have any more questions from the audience. So I want to thank you, Fernando, again, very much. I think it's almost midnight there in Australia, so thank you for being up late to accompany us here. And, well, we'll...
Thank you very much, Fernando.
Yeah.
Good night and good dreams.
We'll do.
Pleasure.
Have a great rest of the conference.
Bye-bye.
Hopefully to meet you in person in Brazil next year.
Also, when are you coming to Brazil?
I'm still deciding. I will definitely come next year. I don't know yet.
So let us know.
We'll do.
So you guys going to NK meeting? So you're going, Fernando, for the NK in Norway?
Yeah.
Oh,
yeah.
great.
I will be there.
So we can
and I will also be in Washington in May for the American Association of Immunology too. I don't know if you're going to be there.
I will not be there. I saw on LinkedIn, and then I said, okay, it will be way too many meetings, so better stop. Otherwise, they will kill me. So they will not kill me. So I need to do more bench work. So that's why I'm not going to another conference. So yeah, but I will meet you guys in Norway for sure. Thank you. See you later.
Sounds great.
Bye-bye.
Awesome.
Bye, Fernando. Thanks so much.
Thank you, everyone.
So we can continue with our workshop. I'm going to introduce the next speaker. Is Dr. Lucila there?
Yes, I'm here.
Hello, doctor. Good morning.
Hello. Hello, everybody.
Thank you so much for accepting this invitation.
Hello.
Hello.
Guys, I'm very happy to be here with you guys, with the invitation. Very nice to be Brazilian shining the world. I think it's so important, right? And do you want me to share my screen?
Yes, please.
Thank you very much for accepting, Lucila, the invitation.
Sure.
While you share your screen, I'm going to give you a brief introduction. So Dr. Lucila Kerbauy is the Medical Quality Manager of Stem Cell Transplantation and Cell Therapy Department at Hospital Israelita Albert Einstein here in São Paulo. She has a residency in medicine at the Faculdade Estadual de Medicina de Marília, and she has a residency in hematology and hemotherapy at Hospital das Clínicas da Faculdade de Medicina here at University of São Paulo. And she did a postdoctoral fellow in bone marrow transplantation and cell therapy at MD Anderson in Houston, Texas, with Dr. Katie Rezvani's group. And she has great researches and publications in clinical trials and research in CAR-T and CAR-NK cells. So please, Dr. Lucila, it's a pleasure to have you.
Thank you so much. I'm just having a little bit problem because I'm not using the Meet all the time.
Okay.
It looks like I need to do some.
Want help to share your screen?
I think yes. If can I send to you my?
Yes.
Just because it looks like I need to. The system preference, something like that.
Okay.
Let me just see. It's saying system preference. I have an issue to. I'm so sorry, guys.
No, you can send me your presentation.
I will just send right now.
And we can share the screen for you.
Great.
So, Lucila, I get the fastest way. That's the same thing that I did with Samuel. So if you do uploading the Google Drive, will be very fast. You can do this very quick.
Okay. Because I'm here in the Google Drive, in fact, uploading the Google Drive.
Yeah. So then you share the link, and then it will be quicker. Sometime. Is she gone? Oh, yeah, she left.
I think she's gonna try to connect again. Let's see. Well, we're still on schedule, so you don't have to worry too much. I'm seeing if she sends me her presentation here. Okay, she didn't send anything, at least for now. Hi, Silla.
You are unmute.
Hi, Lucila, you're on mute. Can you hear?
I sent to you. Yes, sure.
Yeah,
sorry.
I can hear you.
I just sent to you. I think you did you receive the presentation? Not yet.
Let me see here. Just looking at my email.
I will send you again, just in case.
Okay. I didn't receive it yet. I think it's the internet. Let me just wait a little bit.
Yes, I'm sending you again, just in case you will have both. You received twice, no problem.
Don't worry.
But because I think it's a little bit heavy. This is the problem.
Yeah, it might take a few minutes to get here.
There's something regarding the preference. I'm in the Google Drive as well, but I don't know what is happening.
Marcelo, how did you were saying, how did you send the meeting, your presentation?
So I did upload in the Google Drive. So you just drag from your file, and then you drop into the Google Drive. So then from there, then from there, you can, if you open your presentation.
Okay, I have the presentation here, sorry.
Great.
Okay, yeah. Good.
So I will present here, I'll share my screen. And
Wonderful.
Você recebeu, né? Okay, we're gonna share the screen and then you can tell us when we can go past the slides, okay?
Wonderful.
Thank you so much.
Let's just see yes, I don't know why. If I turn on my camera. I
think it's better to leave it off because it might get a little bit slower, the internet. So
Did you share? I'm not seeing it.
Yeah, we're just gonna share it right now.
Okay, great.
Just a minute.
Wonderful. No problem. Sorry.
No problem. We're on time. Okay, can you guys see the screen?
Now I don't know why.
Yes, I can see. Dr.
One second. I don't know because I think I just need to find you here. One second.
Bell is sharing the screen.
I'm not seeing the screen right here. Okay, great.
Yeah.
Okay. So sorry, guys. I apologize this issue. I'm very happy to be with all of you today. It's a great opportunity to share experience and to find other ideas. So today I will talk about novel CAR-NK therapeutics, especially for hematologic and neoplasms. Next, please. This is my disclosures. Next. So here in this table, we can see we have now different products that are available in the United States and Europe regarding the use of the CAR T cells therapy. We have most of the trials was phase 2 clinical trials, pivotal trials that allow the FDA to approve this new treatment. That's because the high you can go next, the high response rate that we can see is between these products. And when you look in the red stars, here we can see the products that the Anvisa, our regulatory agency, are already approved here in Brazil. We don't have everything available because we still need the price of these products, especially for the Axi-cel and the Cilta-cel, for example. But we have these products also available here in Brazil. We can go next. So that's what, but we have different challenges. No, that's perfect. I'm just showing here the response rate of these different products that make these regulatory agencies approve these different products. We can go next. But we have different challenges when you think about autologous CAR T cells. So we are producing cells specifically for each patient. This make that we have a delay in the manufacturing of the cells. So in the left, we can see, for example, in the Belinda phase 3 clinical trials that we use the CAR T, the Guimaraes, to treat patients with diffuse large B-cell lymphoma. In Brazil we have 3 different centers here in Brazil. And when we look, for example, here in Brazil, for us to receive these CAR T cells, took for us around 60 days. And during these 60 days, the patients can relapse. We have a patient progressing and could not really receiving the cells in the best moment. This is costly because we are producing CAR T cells specifically for each patient. We have the patient-to-patient variability because the T cells are different regarding if you're thinking more naive cells or mature cells, depends of the number of treatment that the patient received. And we have especially a lot of challenges regarding the commercialization of the cells because this is a very costly product. In this way, we can go next. We have the possibility to use NK cells as a source for CAR therapy. And this is really interesting because we are thinking about allogeneic product in this sense. So just to remember you already saw a very nice presentation. NK cells are cells from the immune system that express CD56, are negative for CD3. Next, please. These cells can recognize strange cells in the body because we have activating receptors that in the balance between activating and inhibitory receptors makes these cells to recognize strange cells like tumor cells and mediate the killing, different than T cells that we have TCRs that is really specific for each antigen. And next, please. And between this balance, we have the cytotoxicity of the cells, mediating, especially with granzyme B, perforin, trail, in the and then we can perform very good killing of the cells. And also next, the cells can produce other cytokines and chemokines that can communicate with different other cells in our immune system. And also, that is so important for the NK cells is that next, please. The NK cells also has an important activating receptor that is CD16, the CD16A, that can mediate antibody-dependent cellular cytotoxicity. So this is the background, because I will talk about different strategies that we can make NK cells, especially CAR NK cells, better for the treatment of the patients. So next, please. Next slide.
Hi, Lucila, you're not seeing the slides? It didn't go through? Hi, Lucila, can you hear me? I think she crashed as well, maybe. Hi, Lucila. No, I think her connection is bad. Let's see if she returns.
Is she in Australia?
You know why? That's 1st of April. You know, it's a very daring day to do to make meetings.
Is it true?
Yeah, that's Vanderson's idea.
Mine idea.
Okay, I think she's gonna reconnect. Just a minute, guys. Hi, Lucila, can you hear me? You're on mute. Okay, now I can hear you. Oh, she crashed again. She'll reconnect. Just a few minutes, guys. Sorry about that. Hi, Lucila. I think you're on mute.
Bom, não sei se fui eu, provavelmente fui. Tô num lugar, acho que o melhor da casa aqui. Não costumo causar isso. Sorry, everybody. I will continue right now.
Can you see the slides?
Yes, that's perfect.
Go ahead, please.
So we have, as you can see in this table, we don't have so many clinical trials using CAR NK cells yet. Most of them are in phase 1. I think especially we have very few phase 1 or phase 2 clinical trials. The disease is usually we have hematologic disease, so the CAR NK is targeting CD19, CD22, or even CLL1, for example, for AML. And most of them are recruiting right now. So we still don't have data so much data regarding clinical trials using CAR-NK cells, and the source are also different. So we have a peripheral blood as source, umbilical cord blood, or NK92, or even IPS. So different sources are being studied in different clinical trials. Next, please. So talking specifically about the source, we have the possibility to use peripheral blood as source. The advantage is because we have a mature phenotype, very functional and cytotoxicity cells, but on the other hand, we need to have a healthy donor making the donation. We don't have this donor available, and we have the product that is not heterogeneous. We have the possibility to use cord blood NK cells. One important advantage is that we already have different cord bloods already available that is not using for stem cell transplantation. So we could use these cords for other things like CAR-NK therapies, but we have very few number of NK cells when we thinking about 45 mLs of cord nuclease, or even less when you have a 25 mLs bag. So that's we need to have a good strategy to expand these cells to have enough to treat patients. We have the possibility to use IPS, so we can generate these CAR-NK cells in the lab. We will have a homogeneous product, but on the other hand, we have a very mature phenotype with low ADCC. That's why you will see in the next slide strategies to try to make this IPS better. And we can also use NK92, that it is a cell line derived from a patient with NK cell lymphoma that can be used for CAR-NK therapy, but this is a tumor cell line. So we need to radiate the cells, and this is the reason the cells cannot expand after the infusion in the patient, and this is the important advantage to use cell lines as source for NK cell therapy. So next. So this is the reason we have, when I was in the Anderson, we have different studies using cord blood as source, thinking that we have a huge number of NK cord blood available in MD Anderson and here, especially in Brazil. So I was attracted to use cord blood. And the first study, we use a construct to transduce NK cells that has that has CD19 as target. So our SCFV was CD19. The signaling was CD28 and CD30. We also have IL-15 to make the cells to persist better after infusion, and we also have the suicide gene that was the ICASPase 9, because it was the first time you use CAR-NK in patients, so we didn't know if it would be toxic or not. And in the mice experiments that make the FDA approve this trial, so can go next. We can see that the cells that has this construct with IL-15 persist longer in the mice. Next, please. And this makes better anti-tumor effect in the in vivo experiment using NCG mice and Raj as cell line. The tumor was Raj cells. And this is next, please, correspond for better overall survival. So with this data, FDA approved us to follow with the first phase 1 clinical trial. It was the first 11 patient was published in New England in 2020. So we can go next. You can see we transduced the NK cells on day 6 of the manufacturing protocol, and then on day 9 we had the cells already transduced, and they expand using feeder cells, and then the cells were infused fresh after the lymphodepletion therapy of the patients in 3 different doses. So it was 3+3, the design of this clinical trial. And the next, please. And because we have the IL-15, the construct, we could see the persistence of the cells more than 1 year in some patients, even more in the patients that respond to this therapy. And next, we in this publication, the 11 first patient that was treated, we have much more than this right now. We saw that this therapeutic was safe. No, any patient showed GVAG, CRS, or ICANS. The response rate was 73% and almost 70% complete rate. So now we have the phase 2 clinical trial, but we already don't have the data. We are looking for this data. I am very anxious, so let's see if the efficacy of these cells. But we already have the possibility to use IPS as source. So this FT576 cells was a multi-target off-the-shelf IPS against BCMA, but also has the IL-16 humanized receptor, and these cells were modified to express the IL-15 receptors with the IL-15 fusion and the knockout of the CD38. And this data was present in last year. We have 2 different regimens. One in that they infused only the CAR-NK cells that were modified, and the other, the regimen B, they gave the NK cells with daratumumab. And then we have here 9 different patients. And then next, please. And talking very quickly, the patient received a cyclophosphamide and fludarabine, and then 2 infusion of these CAR-NK cells, again, BCMA and the CD38 knockout. And the regimen B, we have the infusion of the daratumumab weekly for 8 weeks, and then twice, we have between 15 days, and then once in a week. And we could see that most of the patients unfortunately progress or have stable disease, but one of them show a GVPR, and this is the data that was present in ASH. So in the next slide, please, we have the other strategy from Fate Pharmaceutical as well, using IPS as well, but in this model, we have the CAR against CD19 for lymphoma, and this data was present in 2021 in ASH, and we can see in this data that the patient that received more than 90 million CAR-NK cells, we have the response rate around 72%, and a complete response of 44%. Next, please. But now we are trying to see better way to make better NK cells. So we are thinking more the NK cells that can express co-stimulatory domain that is more specific for NK cells. So when the Amy Anderson with CD28 and CD30. So now we have studies trying to use 2B4, for example, DAP10, DAP12, that is regulatory domains regarding NK cells. We have a strategy to do knockouts together. We have strategies to transduce the NK cells to expand activity. CARs that is active, is making the NK cells more active, and also CARs that can inhibit the effect of the NK cells. So in this hand, we can provide cells that has less off-target effects. So it's a very interesting thing when we think about, for example, in AML. And we also have the possibility to do cytokine arming NK cells as we did using, for example, IL-15. And also next, we are trying to combine a strategy genetic engineering strategy to overcome suppressors. So, for example, we can transduce the NK cells to express CAR, but also knock out inhibitory genes like TIGIT or NK2A, for example. We have the strategy to knock out proteins that can mediate negative effects regarding cytokines in NK cells. As I show you, we can use the knockout of CD38 or glucocorticoid receptors, or we can increase the expression of chemokine receptors. So with these strategies, we can even think the biology and of the NK cells and trying to improve the anti-tumor effect of these cells. And this was the strategy that we use as also when I was MD Anderson, and May Daher will be here showing her data. But next, please. She handled this project that she had the idea to knock out the CISH, that is a gene that make the expression of the cis. And cis, next please, it's a protein that then can negatively mediate the cytokine, especially IL-15 in the NK cells. So it's a negative cytokine regulator of NK cells. So in this hand, you transduce the cells to express CAR that has IL-15, the construct, and then with the CISH, the CRISPR-Cas9 technique, we knock out the CISH gene, and then we have a very low amount of cis, and this makes the cells more better metabolic, to have better anti-tumor effect. So next, in summary, we can see with this strategy, we can nicely transduce CAR-NK cells, and we can nicely knock out the CISH, and we have here the ELISA showing very low amount of cis, and we in this double changing of the NK cells can provide better overall survival in a NESG RAD cells model, showing better anti-tumor effect. Next, please. And we published recently this paper regarding trogocytosis. So when we think about trogocytosis, we think that the NK or the T cells can have together the receptor that the tumor express. So in this hand, the T cells and the NK cells start to express in the membrane, for example, the CD19, and we proved that this is a phenomenon that happens in CAR-NK cells. So in this case, CAR-NK cells start to express, for example, CD19, and the CAR-NK cells could kill each other, and with that, we have a low amount, reduce the antigen in the tumor, and we have induced self-recognition and killing of these NK cells. So after that, next please, we have the strategy to transduce the NK cells to express CAR-NK cells against CD19, the same construct as we are using in the clinical trial, but also these NK cells express the CAR against CISH, because this is a protein that has in NK cells, and every time the CAR-NK cells recognize the CISH, they will see that it is NK cells, and it has the signal it don't kill. So with this strategy, we saw that the NK cells could persist better in the mice, and this will correspond to better overall survival. So here we can see other strategy to have both one CAR inhibitory that can find cis, and a CAR that is activating against CD19. And then next, please. And then to finish my presentation, I'm showing here a little bit about my PhD. So we have also a way to make better NK cells using BIKE, B-specific antibodies that can recognize CD16, the NK cells, and then the other targets, for example, CD19, CD30. So this B-specific antibody was used before, next please, in a phase 1 clinical trial, a monotherapy, and the next. And then we could see, using as monotherapy, it was safe, but the response was very low. So we didn't see any patient showing complete remission, and only patients showing partial response, or most of them stable or progress after this monotherapy with this B-specific antibody, bispecific antibody. That's why, please, the NK cells from patient Hodgkin lymphoma patient are dysfunctional, as we show can see here, and we show in the publication as well. So we had the idea, next please, to use health NK cells, so allogeneic NK cells from cord blood. These NK cells were memory-like NK cells that we produce in the lab. So we use these NK cells combined with this bispecific antibody against CD30, thinking that in this way we could produce like CAR-like NK cells, but we are not transducing NK cells. We are providing the antibody with the NK cells. So next, please. In this model, it was published. It was my PhD. And then we could show, please, the next, that with this strategy, we gave, after in vitro experiments, we saw that the NK cells can nicely be binding with this antibody. And this binding was really, the cells kept with this antibody more than 72 hours. And then we provide for the mice a model with carpas that express CD30, these NK cells with this antibody. And with this strategy, we saw a nicely tumor control that correspond, next please, to better, next. Yes, to better control of the tumor in the mice and better overall survival. So with this data, this preclinical data, the FDA allow us to move with these phase 1 clinical trials. So we use this cord blood memory-like NK cells with complexed with the FM13, the bispecific antibody against CD30. It was 14 days of production, and then after that we gave different infusion, dose of infusion of this CAR-like NK cells. And then next, please. We had, with this production, we have a very high number of NK cells that were allowed to treat more than 3 patients with one production. And then after that, please, we could treat 41 different patients, and this data was present as our presentation in last ASH. So we can see the median of treatment was 7. So it was a heavily pre-treated patient. We have a patient that also received CAR T cells against CD30 before, and most of them already received autologous stem cell transplantation. And then, so we can see most of the patient already received different treatments, and it was showing the relapse or the refractory disease. And then next, please. This strategy was safe. So we didn't see any case of CRS or neurotoxicity or GVHD. The most of the complication was neutropenia or thrombocytopenias, most regarding with the lymphodepletion regimen. And the dose that we will follow to the phase 2 clinical trial was level 3. So we saw that the higher dose was the better for the patients. And the next, we see very nicely anti-tumor activity. So from 93% of this patient showed response, overall response, is almost 77% complete response. And when you think about the dose that we are now we use for the phase 2 clinical trial, almost 95% of this patient as response. And around 72% complete response. So we have a nicely response with this strategy. And then next, please. So, but some of these patients after complete response relapsed. So this is the reason now we are discussing with the FDA to give more than one infusion of the cells, should give sequentially, as we have a very high number of these cells that we can produce in the lab. We are thinking to give more than one infusion. And I think this strategy will be very interesting, even if you think like a bridge for other treatments. So now we are thinking better strategy to keep this very nice response that we have. And then next. And just to show that we also have here in Brazil different projects to use CAR T cells and CAR NK cells that are in development now in Einstein. Most of them with the Pronon resource have a grant from ASH to do CAR T and CAR NK cells for multiple myeloma. And I hope next year I will show this data, because we already have some nice data. So soon I hope to show to you as well. So to have the take-home messages, we know that the CAR T cells is it's very nicely. We have very interesting data already, solid data with CAR T cells, but we have some limitations that make us think about CAR NK as a good strategy. For now, we have more phase 1 clinical trials with consolidate results. We are waiting the phase 2 clinical trial to see if the cells are safe, but even more the efficacy of the cells. But I think it's really important to have new strategies involving to thinking about checkpoints inhibiting to make better NK cells, and make this strategy to combine NK cells with antibodies, making like CAR-like NK cells. Will show to you that I showed to you. I think it would be a nice strategy. Think about cost, for example. And thank you. I have the last slide just to thank everybody that is helping us in this trial, especially the girls that was working with me in the lab, the cell therapy team, and the Anderson, Einstein, the collaborators, everybody that's helping us with these improvements. Thank you.
Great talk. Thank you very much, Lucila.
Thank you very much, Lucila. We're a little bit behind on the schedule, so I'm gonna make you just one question from the audience, and we can go ahead. So we have a question from Rafael. He asks you, do you think multiple infusions of CAR NK92 cells would compensate for their lack of expansion and be a better approach than using primary CAR NK cells?
This is a very good question. We need to see in the trials, in the clinical trials. I think the better way to think regarding NK92 is multiple infusions, for sure. But I really don't know, because we really want to see some persistence of the cells. This is the problem that we are facing using the cells that is not modifying to express IL-15, for example. So the last topic of my talk, we saw that the NK cells has response, but we would like to keep this response. So I think when you could use primary NK cells that has IL-15 or other cytokine, I still think is a better strategy. So, but let's see the trials. I think it's completely different when we see in vitro or in vivo data in animals and when we move for the trials, right? But if you're thinking about NK92, for sure you should give more than one infusion.
Okay, that's a good answer. Thank you so much, Lucila.
I'm so sorry. I apologize for all these issues, but I will be here.
It was a great
again.
Thank you so much. So I think we can go ahead and follow with Dr. Lee. Dr. Lee, are you there?
I am. Thanks, Samuel.
Hi, Doctor. Thank you very much for accepting this invitation. I'm just going to give a brief introduction, and then you can go ahead with your presentation. So Dr. Lee, he's a professor and director of the Cellular Therapy and Cancer Immunotherapy program in Nationwide Children's Hospital and the Ohio State University James Cancer Hospital. He has leadership positions that include a chair on the Cellular Therapy Strategy Group for Pediatric Blood and Marrow Transplant Consortium. He's a member of the NIH Recombinant DNA Advisory Committee, and he's a member of the Cell Therapy Steering Committee for the Children's Oncology Group. And Dr. Lee's research centers around translational and early phase clinical research of cellular therapy for pediatric cancers. So please, Dr. Lee.
All right. Oh, let me, doesn't look like I'm sharing the right screen here. Hold on.
Okay, it's opening here for us. Okay, we can see.
Can you see?
Yeah.
Great, thank you.
We don't see the presentation yet.
Oh, no?
No, we just see the meeting screen.
How about now?
Okay, now it's great. Perfect.
Okay, perfect. All right. Well, thank you very much. Thank you, Samuel and Vanderson and Lucia, for inviting me. And so let's get started. So, we really stumbled on this approach for growing NK cells because I was a T cell person. We were generating a variety of feeder cells for growing CAR T cells and including the antigen that the CAR T cells would recognize in multiple costimulatory domains. But we found out that it actually initiated very nice, robust expansion of NK cells, as has been shown in a couple other presentations here before. So our basic approach now is to remove T cells so that we don't expand them, grow the NK cells on the feeder cells with about once a week stimulation, and then you have your feeder cells, your NK cells at the end that you can infuse or freeze. And I think a very important part of this that was not engineered, but really just a nature of the expanded cells is that they are very easily cryopreserved and infused, which has been a major problem for many of the NK cell products. So an important part of this was IL-21 and finding that IL-21 allowed sustained proliferation of the NK cells over many, many weeks. We can do this for 8 to 10 weeks, can achieve even billion-fold expansion, although in the clinical applications, we've really just settled on 14-day expansion. It's as many as we can handle in a usual GMP lab, and it's so 14 days is plenty, but really has long-term potential for expansion. So there are many other features of the expanded cells that are important for adoptive cell therapy. compared to proliferation with IL-15 or resting freshly isolated NK cells, they actually make very high levels of interferon gamma, which is quite important for crosstalk to the rest of adaptive immunity. Yes, the NK cells have a direct anti-tumor effect, but it's also very important for these NK cells to talk to T cells and B cells and macrophages and dendritic cells. And that is sets up the inflammatory microenvironment, particularly with this interferon gamma. TNF is also very important as a mechanism of killing targets. So most of what we talk about in NK cell therapy is perforin and granzyme, but perforin and granzyme gets depleted fairly quickly. And so serial killing of NK cells is actually dependent on high levels of this TNF to be present, which is one of the death ligands. And importantly, the NK cells actually start to make some of their own IL-2. And we don't know if this is clinically relevant, but it may mean that they can provide some of their own IL-2 for long-term support. The surface receptors change and these increase very brightly. These have been referred to by Lucia as super bright NK cells or double bright NK cells because they have 56 that is high and 16 that's high. So they don't really look like normal peripheral blood NK cells. They have quite a different looking phenotype. Their metabolic fitness is enhanced. You can see here resting NK cells. This is looking at a scale of 0 to 20, where their glycolytic capacity is somewhere around 10 to 15. And then after expansion, you can see the scale here is 0 to 100, and glycolytic capacity is 70 to 80. So very high upregulation of their metabolic potential. And then one of the important things about IL-21 is it's able to induce telomerase and maintain the telomere lengths of the NK cells so that they have more proliferative potential after adoptive transfer. Their ability to proliferate is often restricted by how long the telomeres are. So the first place that we applied this was in the haplotransplant setting. And we know that, that for haplotransplant, one of the leading approaches is post-transplant cyclophosphamide. And the intent of this chemotherapy is to kill fast-growing T cells that are alloreactive so that you can eliminate GVH. However, in this period, you also have very fast-growing NK cells because NK cells are trying to recover and reconstitute, and the cyclophosphamide also kills those NK cells. So we thought that we might be able to restore NK cell function on this exact platform if we just grew NK cells from the donor and then infused them before the transplant, after the cyclophosphamide, and then again after a month to help restore and advance NK cell reconstitution. This worked very nicely, and in a phase 2 trial, the 25 patients who were treated on here had a marked reduction in relapse rates compared to controls and improved overall survival, less GVHD, and reduced viral reactivation. Importantly, in the post-transplant cyclophosphamide approach, which I just mentioned, the PT-Cy also kills NK cells. At every time point during the transplant, you have T cells that are more dominant than NK cells. And this was confirmed, first described by Luca Vago's group in Italy in this paper, and then confirmed again by Rizwan Romi's group, showing that NK cells were actually, compared to the T cell content, less than half of what the T cells were. However, if you can do adoptive transfer in this setting, we actually did exactly the opposite. We were able to completely reverse the NK cell to T cell dominance and learned that much of this T cell expansion that you see afterwards is very non-specific expansion in response to homeostatic cytokines like IL-15. And if you provide large numbers of NK cells, they use up the IL-15 and further expand. And so you still have fine T cell reconstitution, you just aren't pushing irrelevant T cells. And then by doing this, you're really able to reverse this kind of reconstitution pattern. So in those cases, you're talking about a few doses, but in very discrete periods. I think one of the things that has hurt the field for NK cell therapy has been that people tried to treat the NK cells like T cells. And in T cell therapies, and early NK cell therapies as well, when we were very limited in the number of cells that we could deliver, it was really important to get a single dose of T cells to be your entire therapy. So for CAR T cell therapy, it's very expensive to manufacture. You have to make sure that that product is able to grow in vivo so that you can get enough cells to do something. In TIL cell therapy, it's very hard to grow the enough T cells outside of these tiny little tumor fragments, so you have to get in vivo expansion. But if you can generate large numbers of cells relatively easily, then you can actually give multiple cycles of NK cells, and you can think about NK cells more like a drug, an area under the curve and exposure, and not have to rely, as we were just talking about, on a single infusion's expansion or persistence. So this is really tested in our first trials by looking at adoptive therapy after chemotherapy. So rather than in a setting of a transplant, here we're looking at standard chemotherapy for AML, which is fludarabine and cytarabine, but this would kill off all of the NK cells that are present in the patient, and then you're just waiting to see which one comes back first, NK cells or leukemia. So rather than waiting to do that, can we take this period of lymphopenia that covers about 2 to 3 weeks and infuse as many doses of NK cells as possible and really put pressure on the cancer to not come back? And so this was done by finding a family donor, obtaining blood for them, growing up the cells, cryopreserving them in aliquots, and then each dose is then thawed and infused at the bedside in multiple, very compressed time period. So we initiated 2 of these studies, one where I was at in MD Anderson in the US and the other with Lucia in Brazil. And both studies actually were kind of going on at the same time. Lucia was very wise, I think, in actually allowing some patients who had CNS disease. We were not sure that the NK cells would get there at all, but she treated several patients who had CNS disease. And particularly in this first one, I think you can see that there's relapsed leukemia around the brainstem and the lateral horns. And then about a week after the NK cells were infused, this patient came back into the hospital, had some neurologic symptoms, was admitted to the ICU and had some steroids to calm this down. And then afterwards, all you can see is little punctate lesions of calcification where the leukemia used to be, but he went on for many months to be completely disease-free. So we also know now that these NK cells can cross the blood-brain barrier, which is really an important thing as we come to solid tumors and thinking about both brain metastasis of peripheral tumors as well as brain tumors themselves. So I think it's really important to look at outcomes, and Lucia was able to describe in this swimmer's plot how each of the survivals looked like for the patients on her study. And I'll point out that in the paper from the CAR NK cell study for CD19 CAR cells for lymphoid diseases, the survivals actually look quite similar in terms of response rates and duration of remission. And this is in a plain NK cell that has no genetic modification. There was no IL-15 to push expansion. There was no CAR to help targeting. And I think all of us would agree that relapsed myeloid leukemia is easily as difficult to treat as the lymphoid ones. So yes, I think that the genetic modifications can provide additional targeting, but there's plenty of room for us to think about adoptive transfer of NK cells in the right setting to help the patient's own immune system overcome their cancer just after chemotherapy. So some of the problems with this approach are really about success and cost. So all of these approaches that we've published so far have been with manufacturing patient-specific products, particularly starting with an autologous product that we've completely eliminated now, but then an allogeneic one from a related donor. And the barriers to this are the cost of doing this for each individual patient. I'll get a little bit more into detail on this. At our first studies, this was about $75,000 a patient to do this expansion. We've gotten much better now, but this makes the cost almost not feasible, really, on a larger scale. Now, this is similar cells that they are also very, very expensive, and you have to manufacture every one of them for that patient. There's also some quality potential problems that you can have individual contaminations or too many T cells or high endotoxin or other things that lead you to not release that product. And if you can't release that product for that patient can't be treated. There's time and logistics. It takes time to make these products for special patients, and the patients have to stay alive and be in remission for several weeks, sometimes a month, while you're waiting for their product to be ready. And this is difficult. Sometimes patients progress and can't be done. You also have to have space in the GMP that is ready right when the patient needs it. And sometimes your GMP is busy with other products. There are times when the expansion is poor because you just happen to have a donor that doesn't grow very well, or you have limited starting material. And then last is that you don't have any way to control potency, because every time you're expanding these cells, you're taking a different donor with a different genetic background and different history of viral exposures, and you just have to take what you get. So we've been looking at this about how can we solve some of these problems and make NK cell therapy much more direct and streamlined. And our approach here is really to move to a universal donor product where you eliminate the patient-specific failures of autologous manufacturing, the lack of donor matches if you're doing patient-specific manufacturing, and then selecting a small number of donors that have all the ideal characteristics that then can apply to every recipient. And so we've used the term universal donor very much like the blood bank, where you know that if you have a particular donor of red blood cells, they can be a universal donor to any other blood type. And this is the same kind of concept here. It's not one donor that can treat everybody. It's a type of donor. They meet the universal donor criteria. So we've been working with Be the Match Biotherapies for the last 3 years to identify donors like this. We've defined our optimal donor as someone who has complete KIR ligand mismatch potential, meaning they have C1, C2, and BW4 HLA, and they have all of the inhibitory receptors that go to those HLA, that they are all licensed by having those matches, that they have a high proportion of activating receptors. So we do KIR typing on every donor and make sure that they are able to have those many activating receptors as possible. And then we make sure that they're CMV exposed, so they have history of CMV, and that they have high, because of that, have high NKG2C expression, which is also associated with improved function. And so this kind of donor is about 1 out of 20 healthy individuals, so they're not super rare. You can find them. And it also allows a wide range of flexibility in HLA allele selection so that you can think about overcoming rejection as well. So in the last 3 years, we've collected the donors that I have listed here. We did initial screening of 187 donors. 22 of those passed all of our preliminary testing. The KIR typing CMV status, we did a proliferation test to make sure that donor grows, that they have a high enough percent NKG2C. About half of them, by the time we finally came to be ready, they were either deferred for donor ineligibility, they had positive tests, or else they withdrew. But we were able to collect 10 of them, and there's one more that we're hoping to collect next month. And so you can see what we're able to do here. We collect the blood, we do a CD3 depletion, and then we aliquot the cells into individual vials or bags with a large number, about 1 to 1.5 times 10 to the 8th total cells per bag, with an average of about 30% NK cells. So you can say there's about 10 million cells per batch. In those 10 million cells, we're able to then expand each of those batches in a full optimized process. So what we've been able to do now through this whole period is to go from autologous manufacturing, where we were able to get about 2 doses for each batch. Sometimes we got more, sometimes got less, but the median was about 2 doses per person. When we did patient-specific, we got 3 to 6 doses per batch with enough cells to do 10 to the 8th per kilo. When we optimized that process, we about doubled that. So we got 6 to 12 doses at about half the cost. But then you have times when you have wasted material. Now we have really good manufacturing, but most patients don't need 12 doses. So you finish 6 doses or 3 doses in a transplant, and then the rest is wasted and gets thrown away. So now with this universal donor approach and an optimized process, each batch we are getting 50 to 100 billion NK cells per batch. And with the aliquots that I just showed you, we have frozen. We have now, just in our own facility, we have enough to easily produce at least 6,000 doses of 10 to the 8th per kilo with our current material. And this is now at a quarter of what the cost was, and there's no waste. So on a per dose basis, we're down to somewhere between $3,000 and $4,000 per dose of NK cells, 100 times cheaper than what our CAR T cells are. So Marcelo already talked about TGF-beta imprinting, and I just have one slide to sort of reiterate what we're doing with that. They have higher production of cytokines. They're now resistant to TGF-beta, and this is because of losing SMAD3. They have a changed metabolism profile. They have improved serial killing. And then for solid tumors in particular, we think this is really important that they have a changed Adressin profile. So they have different kinds of chemokine receptors and adhesion molecules that make them a tissue resident phenotype. And so we think that this particular NK cell is going to be much better for solid tumors and able to go into the solid tumor and stay there. So in our completed trials, we've finished 2 autologous NK cell trials. And as I mentioned, those have been difficult with low numbers and high cost. And so we won't be continuing those. But nonetheless, both of those studies showed that it was safe and there were patients with stable disease. Several with haploidentical NK cells, the one I just mentioned with Lucia, the other one that's just being finished up writing that was at MD Anderson, and the chemotherapy one with Lucia. The transplant studies were with both haplotransplant and match transplant and autologous transplant for multiple myeloma. So 2 of those have been published. So overall, through these studies, we've delivered 256 infusions in 117 patients IV and 112 infusions intrathecal in the brain tumor patients in 7 patients. So almost 400 infusions, and none of them have had dose-limiting toxicities yet, even up to the 10 to the 8th per kilo or 3 times 10 to the 8th per meter squared. It's been a very safe infusion, and as I showed you, we've had some very impressive responses. So now ongoing, we only have one other study that is using a haploidentical donor, and this is a pediatric study to try to repeat the haplotransplant experience. We've now enrolled 9 patients on that pediatric study. Everything else we've moved to a universal donor platform and now replicating the AML with FLAG approach in pediatrics and adults and a lymphoma study. And then now that we have this universal donor platform, we can think about doing regular NK cells, TGF-beta imprinted cells, or CAR NK cells. And we have a variety of studies that we're now implementing, particularly with the TGF-beta in the sarcoma and brain tumor field. So I'll just show you a little bit about what we're doing in sarcoma. As was mentioned earlier about the potential for NK cells in osteosarcoma, we started a dog study. It actually is not too difficult to grow NK cells from dogs, and they behave very much the same as the human ones. We can use the same platform, the same feeder cell, and we've been making the same TGF-beta imprinted cells from cells that we get from a blood bank that is for dogs over at Ohio State University. Our treatment plan is to really try to prevent pulmonary metastasis. Our osteosarcoma patients don't die of their primary tumor. That is easy to resect. We have lots of decades of experience in doing that. The problem is recurrence in the lung, and that's where really osteosarcoma wants to go. So we're treating the dogs very early with multiple NK cell infusions right around the time of amputation to see if we can prevent initial seeding that happens during the time of manipulating the tumor. And then after every cycle of chemotherapy, just like the FLAG approach, this chemotherapy is likely to wipe out the endogenous NK cells. So we want to replace the NK cells with infusions after each cycle. So we're doing a dose escalation study here. We've now completed 6 dogs are in our highest dose level now. Here's a historic control, a historic curve of survival with this same carboplatin approach in dogs. And you can see we're now hopefully getting a little bit better than that. But very importantly, I think the animals that we've had so far, these have had no lung metastasis so far. And this one at the end that was the longest one, he actually died cancer-free. He died of a different complication with a GI problem. And so we're now at our high dose level and looking like we've made a significant impact on survival in these dogs. We've just started our human study and we've enrolled now 4 patients. This first patient was treated off study because we didn't have approval yet from, we had approvals, but we didn't have the trial open. And this was a patient with relapsed osteosarcoma in the lung. You can see the lung met here. After 2 cycles of therapy with gemcitabine, docetaxel, and NK cell infusions, you can see PET avidity was completely gone, and the tumor size. This was the tumor growing before at the start of treatment, and then we started treatment with the chemotherapy and NK cells and had at least a 50% reduction in the tumor size. And really for osteosarcoma, this may be a complete response because you don't get rid of all of the extracellular matrix of osteosarcoma. So we're really hopeful about this in the human sarcoma space as well, and really for preventing these pulmonary metastases. So to end, I think now that we've moved on to this universal donor approach, there are really some important questions that we're going to have to answer. And those are, first, is lymphodepletion actually necessary? Or can you give repeated doses instead and really think more about your infusion doses as being your drug and area under the curve rather than a single dose that has to expand ex vivo? Also, is lymphodepletion sufficient? We've been giving a lot of Cy/Flu, and Cy/Flu is really only important for brain tumors and solid tumors for lymphodepletion. But what about modulating the tumor microenvironment? What about actually having an effect on the tumor itself that helps prime it for recognition for NK cells? All of these things are actually beneficial to NK cell therapy, and we should be looking for the best possible platform of chemotherapy to give and not just lymphodepletion. Is allorejection common? Well, we don't really know how common it is in our sarcomas. The patient that I just showed you went for 8 cycles of therapy and never developed rejection antibodies to the donor. We have others that we have treated that have developed some antibodies, but so far, out of a total of about 15 patients who've received universal donor cells, we only have 2 that actually developed rejecting antibodies. So we're not sure that this is really so important. And even if it is it relevant? Because it's very possible that we can change donors to bypass rejection. And this is not possible when you have a single infusion cell therapy, such as a CAR T cell that you're hoping will live for the entire time. So allogeneic approaches in those settings may be very difficult and have to rely on not on overcoming this rejection, where for NK cells, we probably don't. Some of these issues have been really nicely covered by a review article by Lucia that was just published a couple of months ago. And I think it's really important to think about this as you design your clinical trials. And so with that, lots of people to thank. Prior places that I've been at MD Anderson, as well as OSU and nationwide, people who have been in my lab before and now are on with their own careers, and really all the people in the GMP and manufacturing space. And so with that, I'll quit and take any questions if there's any time.
Thank you very much, Dr. Lee. That was a very great presentation. And as we're a little bit behind schedule, is it okay if we go ahead with Dr. Dyer's presentation and we open for questions and discussions after her presentation?
That's great. Yep.
Yeah, thank you so much. Hello, Dr. Dyer.
Hi, can you hear me?
Yeah, perfect. Thank you very much for accepting this invitation.
Yeah, absolutely. My pleasure. Let me just share my slides.
Okay. I'm just going to give a brief introduction. So Dr. Dyer is graduated from the American University of Beirut Faculty of Medicine. Dr. Dyer is an assistant professor and physician scientist at MD Anderson Cancer Center in Houston, Texas. She works at the Department of Stem Cell Transplant and Cellular Therapy, and she has a focus on cellular therapy, gene editing, and immunotherapy to treat cancer patients. And she has great high-impact work and publications, so it's a pleasure to have you with us, Dr. Dyer. Sorry if I mispronounced your name.
No, you're pronouncing it very well, actually. Yes. Okay. Thank you so much for the introduction. It's my pleasure to be here today and talk to you about our work. So what I'll focus on in this presentation is some of the novel engineering strategies that we're employing to enhance the NK cell anti-tumor activity. These are quickly my disclosures before I start. Okay, so there are multiple ways that you can use to enhance NK cell anti-tumor activity. You have heard from Dr. Lee's work about important things they're doing also to enhance NK cell anti-tumor activity. For our program, we're focusing on 3 main areas: the CAR engineering, CRISPR gene editing, and the use of bispecific engagers. So I'll start with CAR engineering. You've heard also about some of the challenges that face autologous CAR T-cell therapy. We all know that CAR T-cells have shown amazing responses in the field of B-cell malignancies and more recently myeloma, and have led to multiple FDA approvals. However, they still have some limitations, including the fact that unfortunately some of the patients progress, or a small fraction unfortunately die while waiting for the manufacturing of their cells. There's also a small risk of manufacturing failure. There's also the issue of the T-cell health. Since we're taking the T-cells directly from the patients themselves, these T-cells have already been exposed to the tumor microenvironment, so they're not necessarily healthy to begin with, which poses some problems. There's also the fact that the manufacturing is costly and logistically cumbersome and takes time, which poses some commercial challenges. So the field is rapidly moving, as you heard from previous presentation, towards allogeneic CAR products as to eliminate this manufacturing time and allow true point-of-care administration to the patients. So when you start from a healthy source or a healthy donor, then you can generate hundreds of doses from a single donor, and then you can freeze the cells and generate biobanks of these off-the-shelf products to treat patients at the time of need. So this can be scaled up to much larger numbers and have a much broader impact on our patient population rather than using the patient's own cells. So in our case, we're focusing on NK cells rather than T cells. NK cells are part of the innate immune system, T cells are part of the adaptive immune system. NK cells are CD56 positive, CD3 negative cells, whereas T cells are CD3 positive, CD4 positive in the case of helper T cells, and CD3 positive, CD8 positive in the case of cytotoxic T cells. NK cells differentiate in the bone marrow, whereas T cells differentiate in the thymus. NK cells do not need any prior antigen priming before they can kill a tumor, whereas T cells, as you know, need prior antigen priming. T cells are very antigen specific in the way they kill through their TCR, whereas NK cells are not antigen specific in the way they kill. NK cells have not been associated with graft versus host disease in the allogeneic setting, whereas T cells have been notorious in causing graft versus host disease in the allogeneic setting. And the way the NK cells kill is very complex. They're very sophisticated cells. They have a lot of activating receptors on their surface, a lot of inhibitory receptors on their surface. And it's the complex integration of the signals that are coming from these activating receptors and inhibitory receptors that determine the fate of the target cells, whether it is being killing or no killing. So some of the advantages that NK cells offer in the setting of CAR therapy over T cells is the fact that, first, as I mentioned, they are not associated with graft versus host disease in the allogeneic setting, and therefore this makes it much easier to generate an off-the-shelf product, which would lower the cost. Whereas in the CAR T-cell world, in order to produce an allogeneic product, you would have to knock out the endogenous alpha-beta TCR in order to decrease the risk of graft versus host disease. NK cells, as I said, kill through multiple ways. So if you engineer them with a chimeric antigen receptor, they can kill through the CAR, but they also can kill through other activating receptors on their surface, such as DNAM, NKG2D, NKG2C, etc. Whereas CAR T cells kill only through the CAR. Therefore, in case of antigen downregulation or antigen loss, the CAR T cells lose their efficacy, whereas CAR NK cells can still kill the target through their other receptors. CAR T cells in the clinical setting have been associated with cytokine release syndrome and neurotoxicity, whereas CAR NK cells in the clinical setting have not been shown to cause these toxicities. They're much safer. So you can generate NK cells through starting from multiple allogeneic sources. You can use peripheral blood. You can use NK cell lines such as NK92. You can use umbilical cord blood. You can differentiate the NK cells from embryonic stem cells or induced pluripotent stem cells. Whichever way you choose, eventually you will end up with a pure population of NK cells that you can then engineer with the chimeric antigen receptor before you infuse patients. So in our center, we focus on umbilical cord blood NK cells. And the first trial that we started in our center, led by Dr. Rizvani in the stem cell transplant and cell therapy department, was this the use of CAR19 IL-15 NK cells. So these are, again, NK cells that are derived from cord blood that we then expand and transduce with a retroviral vector to express a chimeric antigen receptor on their surface. The target in this case was CD19. The vector also includes IL-15 in it to enhance the in vivo proliferation and persistence of the NK cells. Then we expand them for another week. In the meantime, the patients would receive cyclophosphamide and fludarabine for 3 days as lymphodepletion chemotherapy, and on day 0, they received the cell infusion. This was a dose escalation trial. In this particular trial, the cells were infused as fresh cells. So this was not an off-the-shelf product. It was not a frozen product. I'll show you later that we've developed now a freezing. We have optimized the freezing techniques, and now we're employing an off-the-shelf products. But at that moment, it was fresh infusions of NK cells. So this was published in the New England Journal of Medicine. There were very heavily pretreated patients. The phase 1 portion of this trial infused 11 patients. Out of the 11 patients, 8 achieved a complete remission. Again, these were very heavily pretreated patients with multiple lines of therapy, up to 11 lines. Some patients had Burkitt lymphoma, complex karyotype, very, very aggressive histologies, and the overall survival and progression-free survival were very encouraging for this patient population. This is just one example of a patient who achieved a complete remission, pre-admission PET lighting up in multiple areas. 30 days later, after CAR-NK cell infusion, you can see complete resolution of these PET-avid lesions. So as far as the persistence of these cells, the CAR-NK cells persisted, which was very encouraging due to the IL-15 engineering in the CAR-NK cells. So we could detect them up to a year, and it was not dependent on the dose. So at all 3 dose levels, you could see that the NK cells were actually persisting, which was very encouraging. And then we did not see any toxicities in these patients, no cytokine release syndrome, no neurotoxicities. And we looked by ELISA in the serum of the patients, and we did not see elevated levels of IL-6, IL-15, GM-CSF, etc. So this was also very encouraging. So that was published in the New England Journal of Medicine. Now we're trying to expand the platform and target other antigens. So the first antigen other than CD19 we're interested in was CD70. CD70 is a very promising pan-cancer antigen. It's the ligand for the natural ligand for CD27 receptor, and its expression is generally absent on normal non-lymphoid tissue. It has transient expression on activated T cells, activated B cells, and dendritic cells, but it's absent on other normal tissues. And it's been shown that knocking out CD70 does not affect the immune system. So you can still have a completely functional immune system without CD70. CD70 is also constitutively expressed on multiple hematologic malignancies and solid tumors, including renal cell carcinoma, nasopharyngeal carcinoma, multiple lymphomas, and leukemias. And we are interested in developing CAR-NK cells against AML, since our AML patients in the relapsed refractory setting have very poor outcomes. So we wanted to generate the CAR-NK cells that could treat AML patients. And we looked at our AML patients at MD Anderson. We tested 54 patient samples, and we saw that CD70 is actually highly expressed in these patients, and it's not expressed on normal CD34 positive cells derived from cord blood. And the expression of CD70 is very similar to the expression of CD123, which is a common antigen that is being targeted in AML. So we tested these CD70 CAR-NK cells in a THP1 mouse model. This is an aggressive AML mouse model. These are immunocompromised mice, NSG mice, that have been engrafted with THP1 tumor that was modified to have firefly luciferase in it in order to monitor the growth by bioluminescent imaging. You can see that the mice that received the tumor alone rapidly developed tumor. Mice that have received non-transduced NK cells also develop tumor and die, whereas the mice that received the CD70 CAR-NK cells have excellent tumor control. which is quantified here in the B panel, and then this translates to a significant improvement in survival of the mice. So we've done extensive preclinical testing on the CD70 CAR NK cells and extensive IND-enabling studies to prove safety, and this was finally approved by the FDA. And in this trial, we're again deriving the NK cells from cord blood, expanding them with feeder cells and IL-2, then transducing them with the retroviral vector to express the CAR, the CD70 CAR on their surface, and IL-15 again to enhance in vivo persistence and proliferation. Then we expand the cells for another week and bank them as a frozen product. So this trial is different than the CD19 CAR NK cell trial due to the freezing part. So this will be completely off the shelf. The patients would be receiving cyclophosphamide and fludarabine again as lymphodepletion chemotherapy, and on day 0 they will receive the thawed product at the bedside. So this trial has 6 dose levels. 8 million is the lowest dose, up to 4 billion. The 8 million dose is a very low dose. It's even less than what we give to a mouse, but that was mandated by the FDA for safety purposes. So we're starting with this dose level, and there's 2 different basket trials, one for hematologic malignancies and one for solid tumors. And for the hematologic malignancy part, there's multiple expansion cohorts, including a cohort for AML, Hodgkin and non-Hodgkin lymphoma, including patients who have failed CD19 CAR T cells, T-cell lymphomas and leukemias, and multiple myeloma. We have so far infused 3 patients on this clinical trial. We have not seen any cytokine release syndrome or neurotoxicity, and we're starting to see some interesting responses in the patients that hopefully you'll hear about either in AACR or in soon to be conferences. We're also expanding the platform to target CD5 positive T-cell malignancies. So we developed CD5 CAR NK cells and tested them in mice. These are, again, immunocompromised mice, NSG mice that have been engrafted with CCRF, which is a TALL cell line. CD5 CAR NK cells improve tumor outcomes in this mouse model, and you can see it also leads to an extended survival of these mice. So after extensive preclinical testing, we're taking this also to the clinic. Hopefully this trial will be approved by the FDA in the second quarter of this year, hopefully in the next couple of months. Again, this will be a completely off-the-shelf product. There'll be multiple dose levels on this trial. Will be mainly targeting T-cell malignancies, but since some B-cell malignancies also express CD5, such as CLL or mantle cell lymphoma, these patients will also be able to be enrolled on the trial. And the primary objective will be mainly looking at safety and optimal cell dosing. So now I'll move to the second part of the talk, which is focused on CRISPR gene editing. CRISPR gene editing, as you know, has revolutionized the field of molecular biology. It's a very reproducible gene editing tool that was developed by Emmanuel Charpentier and Jennifer Doudna, and they received the Nobel Prize of Chemistry in 2020. It's a very elegant gene editing tool this is very simple. It comprises 2 components: a Cas9 protein, which acts as the enzyme that induces the double-stranded DNA cut, and then a guide RNA, which is a small piece of RNA that guides this enzyme, binds to this enzyme, and guides this enzyme to a particular area of the DNA that you're interested in. So you can really design any guide RNA to target any gene of interest. So the first gene that we were interested in was called CISH. Cytokine-inducible SH2-containing protein is the protein encoded by CISH, and it really acts as a negative feedback loop to shut down a JAK-STAT signaling. So it's induced by cytokines such as IL-15, IL-21, etc. Since these cytokines induce the phosphorylation of the JAK-STAT pathway, CIS acts as a negative feedback loop. It's upregulated to control the activation of this pathway. And it's been shown that ablation of CIS releases a brake on NK cells in mice, enhancing their anti-tumor activity. This was shown very elegantly by Nick Huntington group in Australia. And we wanted to see if our CAR NK cells also have induction of CIS, since our CAR NK cells secrete IL-15, and IL-15 is a known inducer of CIS. We wanted to see if CIS is being upregulated in our CAR NK cells that are expanded in vitro, and we saw that indeed CIS gets upregulated. This was by qPCR. It gets upregulated in our CAR NK cells expanded in vitro. So we designed 2 different guide RNAs to target the exon 4 of the CIS gene, and we obtained excellent knockout efficiencies, as you can see here at the DNA level in the C panel by PCR, and at the protein level by Western blot in the D panel. So then we tested these cells at the transcriptomic level. We saw that CIS knockout CAR NK cells have upregulation of multiple genes compared to unmodified CAR NK cells. And when we did the gene set enrichment analysis to look at the significance of these genes, we saw that there's enrichment in IL-2 STAT5 signaling, JAK-STAT3 signaling, which is not unexpected since CIS is a negative regulator of these pathways. But we also saw enrichment of pathways related to TNF-alpha signaling, interferon gamma response, which are very important for NK factor function. And we also saw enrichment of metabolic pathways such as glycolysis and mTOR pathways, c-MYC, etc., which made us very interested in exploring the metabolomics of CIS knockout. We then tested CIS knockout CAR NK cells in an NSG mouse model of Raji lymphoma. This is a very aggressive Burkitt lymphoma, and it's a non-curative model. And we tested the CIS knockout CAR NK cells in at two different doses, 3 million or 10 million. And at the 2 different doses, we saw that the CIS knockout is improving the outcome of these mice. Especially at the 10 million dose, we saw some mice achieve long-term cures, which was very unusual in the Raji lymphoma mouse model, which is usually very aggressive and non-curable. And when we looked at the tissues of these mice and the bone marrow and liver of these mice, more than a year later, we saw that these mice don't have lymphoma in their bone marrow, liver, or spleen, and unlike the mice that died from that received the unmodified CAR NK cells. So we're also targeting other negative regulators of NK cells. You've heard about TGF-beta in Dr. Lee's talk. We're targeting the TGF-beta receptor 2 on the surface of the CAR NK cells. This was a proof of concept study in GBM, glioblastoma multiforme, which is a very aggressive brain tumor. And we know our group has shown that TGF-beta is very immunosuppressive and very relevant in the context of GBM. So targeting TGF-beta and GBM improves NK cell activity in vitro, and we took also these TGF-beta receptor 2 knockout NK cells and tested them in vivo in a mouse model of glioblastoma, and we saw that they extend the survival of the mice and they improve the tumor control of mice significantly compared to unmodified NK cells. So we're very excited to take these CRISPR gene-edited NK cells and CAR NK cells to the clinic. So for the CAR NK cells, in addition to engineering the cord blood NK cells with the chimeric antigen receptor, we're introducing this large-scale CRISPR knockout approach where we use GMP-grade Cas9, which is the enzyme, and GMP-grade guide RNA. Using a 4D nucleofactor, we have optimize the large-scale approach in our GMP facility, so we can generate large-scale CRISPR knockouts in our CAR NK cells and then expand the CAR NK cells for another week and generate these biobanks of CRISPR-engineered CAR NK cells for off-the-shelf therapy of our patients. So far we have 2 different INDs that were FDA approved with CRISPR engineering, one for COVID CTLs and one for NK cells to treat glioblastoma multiforme. But the next step is to combine this CAR engineering with CRISPR gene editing and take it to the FDA. We're very confident we can achieve that in the coming year. And the third part is focused on bispecific engagers, combining them with CAR NK cells. You've heard from Dr. Kerbauy, who's a dear friend of mine. We actually trained together in Dr. Asmani's lab, so I won't focus too much on this because I'm sure you heard about this from Lucila. So Lucila's work was focused on combining AFM13 with CAR NK cells. So this AFM13 is a bispecific engager. On one end, it binds to CD16 on NK cells, and on the other end, it binds to CD30 on cancer cells such as Hodgkin's lymphoma. So it acts as a bridge. It really brings the tumor cell and the NK cell together to form an immune synapse. And due to Lucila's work, the preclinical work, excellent preclinical work led to opening of a trial led by Dr. Nieto in our department. And really, we've treated, I think, up to 30 patients, if I'm not mistaken. The response rate is up to 90%. These are very heavily pretreated patients, have really progressed on everything, including chemotherapy, brentuximab, nivolumab. Some of them had CAR T cells, and we're seeing amazing responses in these patients. And this comes from Lucila's work. So this is amazing. And then, so I won't take too much of your time because you've heard about that from Lucila. So in conclusion, I hope we convinced you that NK cells are amazing for cancer immunotherapy. You can use them as off-the-shelf products since they're very safe in the allogeneic setting. And we've proved their safety and efficacy in the setting of CAR19 NK cells, and we're now expanding the platform to target other antigens. And we're also combining CAR NK cells with CRISPR gene editing and taking that to the clinic. And we're combining NK cells also with bispecific engagers to enhance their anti-tumor activity. With that, I will end and thank everyone who has been involved in this work. It takes really a village. I thank my mentor, Dr. Rizvani, who trained us, me and Lucila together in the lab, all the stem cell transplant department with Dr. Spall, Dr. Champlin, Dr. Marin, and all the other faculty members, all our research nurses, the GMP facility, all our collaborators in the leukemia and lymphoma departments, and our bioinformatic collaborators, my lab colleagues work very hard in the lab, and all the patients and their families, of course, and all our funding agencies. With that, I will end and happy to take any questions.
Thank you very much, Dr. Dyer. That was a great talk, very interesting. And well, we're going to open for some questions and discussions from the other speakers. And first, I'd like to take a question from the audience for Dr. Lee. And Dr. Lee, Lucas is asking, he's saying that there have been some conflicting results about KIR mismatch exploitation in NK adoptive immunotherapies. So he's asking is there any rationale to prove the efficacy of an universal donor and HLA compatibility selection?
Yeah, so I think it's not really clear, right? We're going to have to do a lot more studies in order to be able to clearly correlate KIR mismatch with responses. One of the things that may be confounding that is the fact that at least for the SIML approach with the 12, 15, 18 activation and for the expansion approaches, that they become so hyperactive that they're relatively insensitive to KIR inhibition, at least in vitro and when we do acute models. Now, after they're adoptively transferred, some of that hyperactivity may settle down and there may be some longer term benefit to KIR mismatch that we'll have to see. But yeah, we don't know if that's actually important, but at least in our past data, it's been one of the predictors, so.
Okay, great, thanks. And this one is addressed to all NK specialists here. So he's asking why GVHD is not induced in allogenic NK cell adoptive therapy, considering that KIR alloreactivity and the activation status of the infused cells.
So I think I can take a stab at that. So I think KIR alloreactivity is a little bit of a wrong name. It's what we have, but cells are not alloreactive through KIR against HLA. They're disinhibited, and disinhibited does not mean activation. So NK cells have to have both. They have to have an activation signal and be released from inhibition. And normal tissue does not provide an activation signal. There's no presence of MIC-A, MIC-B, the ligands such as PVR. You don't have antibodies stuck onto normal tissue. So there's nothing to provide an activation signal. And the lack of inhibition is not sufficient to cause activation.
Yeah, absolutely. I second Dr. Lee, of course, who's an expert in the field. It's just that on normal cells, in NK cells, the inhibitory signal is so much more dominant than the activating signal. So it's there to safeguard us, basically, to make sure the normal cells don't get killed by NK cells. So it's like it's really the holy grail of immunotherapy, that they attack tumor cells, but they really are very safe against normal cells. They cannot kill normal cells, NK cells, which is the beauty of NK cells. They're very safe in the allogeneic setting. And due to this, the fact that the dominance of the negative signal, since there is HLA class 1 on normal cells, it binds to the inhibitory gears, and that dominates over any activating signals that could be expressed on normal cells.
Okay, that's great. I have another question for Dr. Dyer now from Rafael. He's asking, what is your opinion on the safety and feasibility of CRISPR-Cas versus lentiviral methods to create CAR-NK cells? Do you think CRISPR may eventually replace the lentiviral method as a main choice?
So I can tell you from my experience, CRISPR gene editing, taking that to the clinic is very, very difficult. Like, we've had so many issues with the FDA, back and forth to actually prove safety. It's becoming more and more strict to make sure, because it's a gene editing approach. So you can induce a lot of off-target things, unwanted things. So to prove that you're not causing these unwanted things, you have to do so many IND-enabling studies. So it's really very difficult to convince the FDA that this approach is safe. So the lentiviral and retroviral approaches have been there for a really long time, and it's much easier to take a CAR-engineered product through lentiviral or retroviral approach to the clinic. It's now something very easy to convince the FDA that it's safe, especially for CAR-NK cells. But for CRISPR gene editing, it's a much harder thing to try to convince the FDA. For CRISPR knockout is one thing. CRISPR knock-in is even a more complicated approach. So I don't think it will, in the near future, replace our regular methods of transducing CAR-NK cells with viral vectors.
Very interesting. And do you think that even with the recent gene therapy products for sickle cell disease, this isn't going to help the FDA to make this process faster?
It's still very difficult. We thought it's going to be easy, so let's do it. We've been trying to do it for the past 5 years, and then for the last year, we finally had 2 INDs that were approved by the FDA. It's still very, very hard. It's actually getting harder with time. It's not getting easier. The more we know about the off-target edits that can happen with CRISPR, the more the FDA wants you to prove with multiple methods that you're not inducing these unwanted edits in the genome. So it's getting harder to get these products approved by the FDA.
Okay, that's interesting. Dr. Lucia, do you have a question?
Yes. Are you listening to me? Okay, I thought I had dropped again. I have to go to the farm. There is better. Here in the city is very bad, the connection. But I think a universal donor is an completely ideal, situation for cellular therapy product. I have although I have some doubts because, you can keep cells from cancer cells like K562 or whatever cell. You can keep it in a bank, a master bank. And I wonder how many times can you get, I think that's a draw. It's not something that will not allow to utilize. And I hope we're going to go to a donor, to a universal donor. But how to do it from one donor or for 6 donors, how are you going to maintain it in a normal cell development? I don't know. Was I clear? You were mute, yes.
Yeah, so I think there's some importance to differentiate a universal donor approach the way that companies that use iPSCs have defined versus what May is doing at MD Anderson with cord blood or what we're doing with peripheral blood. And we're not expanding the cells or keeping them in culture any longer than we would normally for donor-specific manufacturing. And the key is in finding sufficient rationale and criteria for your universal donor that you can continue to find those patients in the population. For us, since it's only 1 out of 20 individuals, we can readily go back and actually find more of those donors easily. And for May and their group at MD Anderson, they have a large cord blood bank to draw from. So as long as we're not culturing them for a very long time, like with Fate, it's really 2 to 3 months of culture by the time you get your primary iPSC differentiated to a early product and then redifferentiated to NK cells and then expanded, and everything has to come from that single cell. I think that's where there may be more issues, although so far they haven't had any problems.
You're on mute, doctor.
Thank you very much, Dean. I lost you in the middle because my connection is really bad, but I'll talk to you. I'll go after you.
So I have one question, I think. First of all, thank you very much, Dr. Dyer, Dr. Lee, Dr. Kerbauy. It has been really, of course, Marcelo and also Fernando. So it has been a really very nice workshop on NK cell. I have one question, this concerning what you have just mentioned, Dean, about would you prefer, and also Dr. Dyer, would you prefer to do cord blood and how to choose the cord blood to produce CAR-NK? And if, do you think the universal donor, if you compare NK expanded versus CAR-NK, what do you think it will really matters? Because, we have in Brazil and all over the world, we are very worried with the price, with the costs. And of course, this is a big problem to use CAR T cells or even CAR-NK in the future. So if you think, would you comparing CAR-NK with expanded NK, what do you think it will really gain in this battle?
I'll let Dr. Dyer start on this one.
Sure. So, so there are 2 parts of your question, if I understood correctly. One is, what's the advantage of introducing a CAR rather than just using NK cells that are expanded, right? And the second question is advantage of the donor, like the source, cord blood versus others, for example.
That's it.
Okay, so I'll tackle the first part, which is why do CAR-NK cells versus regular expanded NK cells, right? So regular expanded NK cells in our center, we've tried to use them before, and many other centers and many other researchers have tried to use expanded NK cells without CAR engineering. And the results of adoptive NK cell therapy without CAR engineering, without cytokine engineering, are, we're not very encouraging. And that's why NK cells were in the shadow for a long time without this cytokine engineering, because the persistence of NK cells in the patients is not good. Okay, without cytokine engineering, they can persist up to 3 weeks, I would say, and then they go away. So you would need multiple infusions, which not necessarily, eventually it would catch up on the cost, right? If you're worried about the cost. So you would need multiple NK cell infusion in order to have some anti-tumor activity because of the issue of lack of persistence. So it's much better to actually engineer the NK cells with cytokines, at least. If let's not talk about the CAR. CAR is another level, but you need this cytokine engineering such as IL-15 in order for the cells to persist so that you can give the patients even one infusion and have a long-term improvements in outcome. And we're seeing with even one infusion that IL-15 engineering actually improves the persistence significantly. As you saw from the talk, we are seeing these NK cells persist up to a year and even more in the patient's black qPCR at low levels in the blood. And these NK cells also traffic to areas of disease, so you can find them in tissues, right? So cytokine engineering, in my opinion, is essential for NK cell anti-tumor activity. Is very different than T cells, because T cells can, persist longer even without cytokine engineering, develop memory, etc. The NK cells need this IL-15 or other cytokine engineering for it to persist. So that's one. CAR engineering is just another level to have some more specificity of killing. Since NK cells do not kill targets in a specific way, the CAR introduces this capacity, gives the NK cells this capacity to kill the tumor in a specific manner, in addition to the other way of killing tumors in a non-specific way through the activating receptors. So CAR is just another level, but if you want to start with something, cytokine engineering is essential. Second, cord blood versus other sources. In my opinion, there are multiple sources. The source is not as important as the actual process that you will do to the NK cell with the engineering part. So you can get them from healthy donors, you can get them from cord blood, you can get them from iPSCs. We're seeing responses. Fate Therapeutic is seeing responses. We're seeing responses. No matter what the source, NK cells are safe. So whatever source is available to you, we chose cord blood not because cord blood is much better than the others. It's just due to convenience. We have the cord blood bank here that Dr. Spall, who's the head of our department, has headed the cord blood, and it's just very convenient for us to get cord blood and derive our NK cells from cord blood. So I don't have like a specific, I will not say, oh, cord blood is much better than peripheral blood, or cord blood is much better than iPSCs. What I can tell you, cord blood has a lot of diversity. We've published about that. NK cells derived from cord blood have a very large diversity compared to NK cells derived from peripheral blood, for example. So it has some advantages, but it's not, I wouldn't say it's much better than any, and you should do cord blood rather than any other source. Whatever source is available to you and is easier for you, go with it.
EJ would be very happy if you could say this, if you could say that cord blood is the best. But my question is also, as Dean has shown, the universal donor, what about because I remember blood transplantation for many, many years. At the beginning, we're choosing the cords to do CAR NK based on some requirements of HLA. So now you do not do this anymore. But of course, we know that there are, a limitation of the number of cells. There is probably because the product of cord blood is a frozen product. So what, in terms of In terms of technical problems, what have you been facing with cord blood?
Yeah, so there's a lot of donor-to-donor variability with cord blood. So some cords are much better than others in number of NK cells, capacity of the NK cells to expand, anti-tumor activity of the NK cells. So definitely we're facing that in the preclinical setting and in the clinical setting. So we're trying to understand what makes a cord blood a good cord and what's making a cord blood a bad cord, because there's definitely, we've seen that some cords we can generate NK cells that are super killers, and some cords give us NK cells that barely kill. And we don't fully understand it yet. We're doing systematic, approaches to try to understand this at the transcriptomic level, at the proteomic level, at the epigenetic level, because there's a lot of things going on in the microenvironment of the cord blood. These are, depending on what the baby has been exposed to, if the baby, was a male versus female, if the baby had an infection, if the baby, there's so many factors that could play into making these cord bloods good or bad cords as a source of NK cells. So it's a very complex topic, and we're still doing a lot of research to understand that. It's not a final thing, but we are looking into it.
And what about you, Dean? What do you think about this?
I think every platform has pros and cons. And so we just have to learn what they are and overcome them. So we have, donor-specific differences, and so we're trying to overcome that by trying to define what that donor should look like. There are some advantages to peripheral blood in terms of being able to collect very large numbers of cells and go back to those donors for repeat donations. But there's also disadvantages in terms of they're already mature, and there may be some, depending on your genetic modification approach, cord blood cells seem to be a little bit easier in some settings. I think from a CAR versus wild type, it depends on the application. I think we've found some circumstances where non-modified NK cells have a role, but there are many tumors that are quite resistant to NK cells unless they are modified. And so the addition of targeting to an NK cell is really important. Whether or not that targeting is through an antibody, a bispecific, a trispecific, or a CAR may not matter, but we're going to have to find out which of those can be applied in the clinic best. For a long time, I left the CAR field because I thought, well, a CAR is actually a way to make a T cell behave like an NK cell with an antibody. So if you already have antibodies, why go through the problem of getting a CAR? But there's probably some rationale for doing it in some contexts. So, but targeting is helpful depending on the tumor.
Very good, thank you. Lucia, the last question, because we
Yes, I would like to, more than a question, I would like to make comment some things. There isn't in the literature of any trial done with NK cells that persistence and expansion has to do with clinical efficacy. So I have this problem to look at NK cells like it would be a T lymphocyte. So T lymphocytes are known to expand, and that's the beauty of the adaptive immunity. While are you listening?
Anymore. Not anymore. Well,
yeah. She said her internet is not good today. Yeah, she'll come back in just 2 minutes. Yeah.
Are you in Australia, Lucia? You are unmute. We cannot hear you.
I wish I would be. But I have this problem, there isn't. I recently reviewed every single trial, and there is none that expansion and persistence had being linked to efficacy. So I that's my commentary. I have doubts if we, again, have to look to NK cells as if they were T cells. And although, the ideal, I still think would be great, and I hope we are waiting for you guys to develop a universal donor so we can learn how to do it, but that's what I want to make this comment, because, I think it came from, I don't know where, the thing that NK cells have to persist and expand. I don't know. Just make this comment. I would like to hear from you.
So it's indirect, right? The fact that none of the studies with NK cells early on had any positive outcomes until they did lymphodepletion. But it's not entirely clear that it was lymphodepletion that the connecting the dots between lymphodepletion, expansion, persistence, and outcomes is still loose. I think another consideration may be, in what context are we giving NK cell therapy? Mm-hmm. For our sarcoma studies, we're giving cycles of chemotherapy with NK cells in each cycle. If you're going to give cycles of chemotherapy, then your persistence doesn't matter because you're going to kill the NK cells anyway. So there may be settings where we don't need to engineer or push for persistence because of what our baseline therapy is. But I think, like what T cells have shown, if we can make an NK cell that has long-term survival and function, those may have very good function. We just need to prove them. So we're not going after that in ours, but I can see potential. So
okay, so
now it's Vanderson. That's
I think it's time.
It's the 1st of April.
1st of April.
That's a problem.
Thank you very much for everybody, speakers and all participants, and have a nice lunch because it's time to lunch. Everybody's hungry. Thank you very much, Marcelo, Dr. Daya, Dr. Lee, Lucila, and Lucia, and all the speakers, and Fernando, who has left already. And Samuel for organizing everything. Thank you very much, Samuel.
Thanks.
Thank you all for the invitation.
Thank you very much.
Thank you. Bye-bye.
It was very nice.
It was wonderful.
Nice day. Bye-bye.
Bye.
Samuel for organizing everything.